Okay, good evening. Good evening, can you hear me? Good evening. So yesterday we have seen the small signal analysis, right? So we mentioned that a signal is qualified to be called as a small signal only when the signal is kept much less than VT. VT being 25 millivolt, your signal should be much less than 25 millivolt. That is when the signal is qualified to be called as a small signal, right? And before applying the signal, you have to add a DC of 700 millivolt or 0.7 volts. And then over that DC, if there is a small signal, then the nonlinear device can behave as linear because the perturbation over that characteristic is going to be very small. You're going to utilize a small portion of the total characteristics, right? Not the total characteristic, only a small portion of the total characteristics. Then the device that is nonlinear is now tamed to behave as linear, right? Okay. Now suppose I have an amplifier, VTC characteristics, voltage transfer characteristics. An amplifier has a transfer characteristics, voltage transfer characteristics given by voltage transfer characteristics given by V naught equal to 10 minus 5 into V in minus 2 whole square. So this is something like, right, even the MOSFET is going to give you a square law. It's a square law device. So there's some sort of a nonlinear relationship between V naught and V in. But in spite of amplifier having a nonlinear characteristic, if the signal is kept small, then it might give you a gain, right? It can give you some sort of a gain, a linear gain. So V naught is 10 minus 5 into V in minus 2 whole square, defined for 2 is less than or equal to V in is less than or equal to V naught plus 2. So there's some value, right? Now what you have to do is find your V in DC. V in DC. If your V naught DC, you're operating at 10 volt. Oh no, 10 volt is the extreme, right? We'll make it 5 volt. V naught DC is 5 volt. The second thing is calculate delta V naught by delta V in. What is delta V naught by delta V in? It's called AV. What does AV stand for? Voltage gain, right? So calculate V naught by V in, which is AV, at this operating point. At this operating point. So you have an amplifier with a nonlinear characteristics. You have to first find the operating point, and then at that operating point, what is the voltage gain of such an amplifier? Okay. So did everybody settle down? Right? Yeah, good evening. Good evening once again. Good evening. Okay, so how do you solve this problem? So this is the nonlinear characteristics. What is V in if V naught DC is 5 volt? So you can substitute, we have V naught equal to 10 minus 5 into V in minus 2 whole square. All right. Here, if your V naught is 5 into V in minus 2 whole square. So from here, what is V in? 10 minus 5, 5 by 5, 1, root 1 is 1. So it should be 3 volt. Am I right? So your V in DC is going to be 3 volt. So this is A bit. Or if you want, you can draw the transfer characteristics from here. Let's draw the transfer characteristics. Transfer characteristics. What if V in is 2 volt? If V in is 2 volt, because it's defined between 2 volt and V naught plus 2. So I'm putting V in equal to 2 in this equation. I'm going to get V naught equal to 10 volt. 10 volt. And then V in is V naught plus 2. So if V in is V naught plus 2, what is V naught? Just tell me in this equation, if I substitute V in equal to V naught plus 2, what is V naught? That's a quadratic, right? V naught plus 2 minus 2, V naught square, 10 minus 5 V naught square. So V naught equal to 10 minus 5 V naught square. So please tell me, somebody can solve that? And V in is V naught plus 2. Then what is my V naught? So just give me this V naught value before I draw the characteristics here. V in on x-axis, V naught on y-axis. If V in is 2 volt, your V naught is 10 volt. 10 volt. And after that, this is a square law. So how much is this here? If your V in is, what is V naught? V naught is something like 3.3 or something, 3.3. Solve it. Then if this is 3.3, 3.3 minus 2, 1.3. Okay. So I'm just drawing the transfer. It's not necessary because we have already solved the problem. What is the problem here? V naught is 10 minus 5 into V in minus 2 whole square. The operating point is at V in equal to 3 volts. This is the operating point. This is the operating point here. Five volt. This is 3. We have already done this, right? So we calculated it here. The operating point is when V in is 3, your V naught is 5, right? So your V naught is 5 when your V in is 3 volt DC. So this is also called the Q point. It is also called the Q point or operating point. Now at this operating point, what is B bit? They say that they want to apply a signal here, and when they apply a signal, they want the gain. They want the gain. So if I apply a signal here, say this is my positive signal. So when my input is positive, what is my output? If my input is positive, so in this gap, I'm going to get, right? And when my input is negative, so this is here. So when I apply a signal, I'm going to get 180 degrees phase shift, right? So let's see. The B bit says that calculate AV, which is delta V naught by delta V, or dV naught by dV. So what is differentiation of this value? If V naught is this, what is dV naught by dV? It is minus 5 into V in minus 2. Am I right? What is differentiation of x square? Differentiation of x square is 2x. So 5 into 2 is going to be 10. Am I right? So it's minus 10 into V in minus 2. Minus 10 into V in minus 2. But what is V in? V in at the operating point is 3 at the operating point. V in is 3. So when I substitute 3 here, my voltage gain is going to be minus 10. My voltage gain is going to be minus 10. See, this is the headache with mathematics. When an amplifier is given, if you draw the characteristics, then you have to apply calculus. Instead, what we do is the slopes we have yesterday we have seen the slopes we have converted them into resistors. Do you remember? Right? So the moment you find a diode, what did we do? You have to replace whenever the voltage changes, the current will also change. So it's like Y equal to mx. You know x and you want y. If you know x, you want y, then you have to know m. So that m or 1 by m is that value of resistor. So whenever a device is there with a certain characteristic, it's always easier to replace the slope or 1 by slope with a resistor value. But now here we don't know what device it is. The examiner, he just has given a relationship between the input of an amplifier and the output of an amplifier, and said that if this amplifier has some sort of transfer characteristic, he is fixing an operating point at V naught equal to 5 volt. So at V naught equal to 5 and V in equal to 3. At that operating point, if you apply a small signal, then the output is going to be 180 degrees phase shift because of the negative slope here. So you can see the negative slope, right? So from here, from all the way to 10 volts to almost 3.3, almost 0 down, you have a slope, right? So naturally, if you're operating here, if you're operating at this point, right? If you're operating at this point, yeah, this is my line. So as long as the signal is kept small, so that line is going to look as linear. It's going to look as linear. And because of the negative slope, you're going to get minus 10, right? Even common emitter in future is going to have a negative slope, right? Where if you draw the transfer characteristics, that's the reason when you apply a signal, it always flips by 180 degrees, right? Okay. So which is easier, by model is easier, or with calculus it is easier, right? It's always with the equivalent model, right? So because for one device, okay, we can go with the characteristic. What if a differential amplifier is there it's got 4 transistors, and that is biased by current mirror. That is again 2 transistors. Suppose there is a 6 transistor problem. What will you do? Will you keep on drawing every characteristics of the device and then superimpose and then get an operating point? That's not possible. That's not possible. Instead, we replace each device by its equivalent model. That is better. Slowly, we will do it intuitively. Even 6 transistors, by looking at the circuit, we will intuitively understand the model and we will directly tell the answer by inspection, right? But everything came from mathematics. So from the characteristics of the device, then with an equivalent model. Are you getting? See, this is the modeling is so popular in every field of engineering. It's not only electronics. I have seen mechanical engineers. There is a subject called heat transfer, right, for mechanical guys. So it so happened that the mechanical sir was there just beside me. We were having food together, and suddenly I just opened his book, right, with his permission. I found only resistors in that book. I got shocked. Then I asked him, are you teaching some electrical engineering or electronics? He said, no. The subject is heat transfer only. And it is only because of you guys, you electronic guys, our heat transfer subject has become simple. I got surprised. How a heat transfer subject becomes simple? Because of resistors. He said that the temperature, the heat transfer, suppose if it's a voltage, the temperature if it's voltage, the heat transfer is like the current, and the ratio between the voltage and the current is the temperature gradient. So all these resistors, they write resistors in parallel, resistors in series, they are representing some sort of relationship between the heat transfer and the temperature. For us, resistors represent the relationship between voltages and currents. So basically, it's nothing but Y equal to mx, V equal to Ri. As long as V equal to Ri, R stands for what? The constant there, which is the ratio between the voltage and the current. For them, it's different. So if you open the book, only resistors in series, resistors in parallel. But what is the final outcome? The final outcome, he's explaining, how heat is transferred from a bucket of water. So to explain heat transfer from a bucket of water, he has resistors there. What do I have? I will have resistors to explain complicated nonlinear devices like the diode, BJT, and MOSFET. So I'm going to replace even BJT with resistors, MOSFET with resistors, and that's how we are going to simplify things, right? Okay. Okay, you just try to calculate this. I'm not quite sure. I'm just vaguely remembering, right? So you can solve the quadratic equation here. If V in is V naught plus 2, right? So it's V naught equal to 10 minus 5 into V naught square, right? That is okay, fine. It doesn't matter. This node doesn't matter. What matters is dV naught by dV in, right? Okay. And please don't do V naught by V in, right? Don't do V naught by V in. 5 by 3 you should not do. Are you getting? Always remember voltage gain, current gain, input resistance, output resistance, all these are signal parameters or AC parameters. So they are calculated only from slopes. They are calculated only from slopes. You should not do 5 by 3 like that. Are you getting? 5 is the DC voltage, 3 is the DC input voltage, 5 is the DC output. The ratio is not going to give you voltage gain. Voltage gain is always dV naught by dV in. When my V fluctuates by a delta X amount, my V naught is going to fluctuate by delta Y amount. So the voltage gain is going to be small V naught by small V. It is nothing but what? A small V naught by small V, which is delta V naught by delta V. That is nothing but dV naught by dV. It is going to be dV naught by dV. So the voltage gain is going to be minus 10. Okay. Fine. Forget about the characteristics. The A bit answer is 3 volt and the B bit answer is minus 10. Okay, so let's start BJT and its a region of operation. BJT and its region of operation. BJT stands for the bipolar junction transistor, right? The bipolar junction transistor. Now, yesterday we have seen the small signal analysis of a diode. And for a diode, what is the voltage and the current that I've given? I've applied some voltage to a diode. So this voltage was, if I remember, 2 sine omega t millivolt. It was 2 sine omega t millivolt. So the dynamics is 2 sine omega t millivolt. So when the voltage changes by a millivolt, we have found that the current here is around 1.9 sine omega t microamp. So if I apply a millivolt signal, I'm going to get microamp. So with this, what amplification can we do, right? So we can't do anything great with a 1.9 sine omega t milliamp, right? Now, we are going to introduce a device now, and this device peculiarly has some sort of behavior. For example, if I give the same 2 sine omega t millivolts, I'm going to get, I mean, this device also has a diode here, doesn't matter. And I'm going to get 1.9 sine omega t micro here. But this device is peculiar that whenever a current flows here, there is going to be another current coming from the supply here. But this current is going to get multiplied by some factor, 100 times of this small current, right? Something like beta or something like that, right? Beta IB. So whenever there's a microamp, the micro is going to convert into milli. But when a milliampere flows through kilo ohm, then you have a millivolt signal, and then there's a microampere of current, and then the micro is converted to milli, but the milli is going to give volts, right? So it's different. Now this device is something which we are going to inspect carefully, but this device can be used as an amplifier, but a diode cannot be used as an amplifier, right? A diode has, if you see the dynamics in the diode, when I apply a millivolt signal, there's only a microampere of current. But in the device that we are going to discuss now, if there is a microampere of current at the input, there's going to be a milliampere current at the output. And when that milli flows through a kilo ohm, you're going to get volts. So this device somehow is going to do amplification, right? So we will inspect this device carefully. I'm just giving you the numbers, right? How it does and all that we will see, right? So let me tell you, a diode is a nonlinear passive device. Passive device, because there's no separate built-in source of power like the VCC supply here, right? But a BJT is a nonlinear active device. Active device because there is a built-in source of power, right, for BJT. Okay, fine. So who is a better amplifier now, a diode or a BJT? Who is a better amplifier, a diode or a BJT? So obviously a BJT is going to be a better amplifier. But who is a better switch? Who is a better switch? Do you think a diode is a better switch or a BJT is a better switch? Who is a better switch? Who is a better switch? Who is a better switch? Now, suppose I have a switch here and there's a bulb and I connect 5 volt. I have a switch, there's a bulb and I connect 5 volt. Now, what is the best way to control the flow of current through the bulb? When you close the switch, the current is going to flow and the bulb will glow, right? If you open the switch, the bulb is going to get off. So you have to do it manually, right? You have to do it manually. So you have to close the switch or put off the switch, open, right? But can we do it standing in a remote place? That'll be more fun, right? Just stand at a remote place and you clap. If you clap, the bulb should glow. So can it ever happen that you just clap and then the bulb glows, right? So that's more fun. Now, how can I do that? Now I'm standing at a remote place here and I have a bulb. I want this bulb to glow the moment I clap from here, right? Just clap, the bulb should glow. Now, can it happen? Let's see. So I'm giving the same 5 volt here, 5 volt. And I want the switch to close here when I clap. So I want the switch is put here between the 2 points and the switch should get closed when I clap, right? So how do I do that? How do I do that? It's simple. I'm going to put a device like this, and here I'll connect a microphone, and just to increase the average value, I'll put something like a rectifier, and then I clap here, right? If I clap, what will happen? The sound is going to convert into an electrical signal, right? And the rectifier is going to increase the average value. And somehow, if you can provide a 0.6 volts or 0.7 volts at this point, then the device is going to get on and the current is going to flow. The current is going to flow. So, in my opinion, a diode is a switch, but a BJT by far is much, much sophisticated than a diode. A BJT is a control switch, is a controlled switch. Is a control switch. Now, how does he do that? You know, just think about a while. What is the operation of a BJT for which this is going to happen, right? So what is a BJT made of? What's there inside a BJT? What are the terminals of a BJT? What is the emitter? What is a base? What is a collector? So what do they do? What is that package doing such that you clap at one point and the bulb starts glowing? Okay, so what is this BJT made of? A BJT now this is an NPN transistor. It is an NPN transistor, NPN. So you have a emitter here, right? So this is the emitter. There is base and collector. So this is the base terminal, emitter terminal, and collector terminal, right? So you have three terminals, and the collector terminal is connected to a bulb. It's connected to a bulb, and here you have given 5 volt. 5 volt. This is ground. Emitter is already grounded. Now, how's that if I just clap from here, the bulb is glowing, right? So what is happening there? Now we know that the emitter, the N material, the majority carriers in N material are electrons, right? They are electrons. And for P material, it is holes. So whenever there is a PN junction, there is a barrier here, right? So this is something like a barrier. There is a barrier, and this barrier, somehow, if you can provide a 0.7 volts here, right? By external means, if you can provide 0.7 volts, then what will happen? It so happens that the electrons from the N material, now they go to what region? The base region, right? So you have holes here, you have electrons here, and there is something called, once the barrier breaks, there's something called the recombination. So in recombination, the clever idea here is the base width is kept extremely small, right? So what happens if suppose I want emitter current and the collector current to be same. I want the emitter current and the collector current to be same. So I'll keep base width so small that suppose if suppose 100 electrons start from emitter and reach base, only one should die, right? It's like 100 soldiers have started their journey, and once they reach the base terminal, only one will die because there are holes and electrons. So during recombination, so one will vanish. But still, all the electrons from the N material, they have reached P. They have reached P, right? Now, these electrons are negatively charged. These electrons are what? Negatively charged, and they get nicely attracted towards the positive terminal. So if you want the electrons to get attracted towards the positive terminal, first you have to break the barrier. That's all. So it's the same thing as a diode. There's nothing great between a BJT and it, but the only trick here is the base width is kept extremely small. When you keep the base width extremely small, all the electrons from the N material, they reach P region, right? So in P region, once they recombine, very few will die, and still you're left with the whole numbers was 100 travel, you're still left with 99. These electrons are negatively charged, so they get nicely attracted towards the positive terminal. So this is a great idea, right? Great idea. Brattain, Bardeen, and William Shockley, right? These three guys, they have invented the transistor. They're simple. So if you don't do, I mean, the moment you clap it, you're somehow supplying 0.7 here, and you break the barrier. So once you break the barrier from a remote place, so that's the benefit of having three terminals. Previously, unlike a diode, who was switching on a diode? The diode is totally switched on by the voltage that we are giving, right? So it's not like externally we are doing it. So it is on because of the supply, right? But here, this is a diode here. This diode, externally we are making it on. When you make it on, naturally there is a flow of current through. So this is a normal diode. This is now a control diode. This is like a control switch. A control switch. So you somehow supply 0.7 volts, and then all the electrons from the N material, they reach P and get attracted towards the positive terminal. Now, the question is, any high school student will give this explanation, right? So what's the big deal in that? Electrons are there, N material is there, P material, N material. So all the, whatever you emit, you have to collect it, right? So from the emitter, they go and reach the collector, and that's the current in the loop. Now, any high school student will explain this, but in analog, with this idea, you cannot do anything. You cannot design any analog circuit by putting all these dabba here, right? One electron, hole, barrier. So what is happening inside, if you keep on brooding it, all this is useless in analog. In analog, what we need is, we need 4 combinations. We need 4 combinations of this circuit behavior. For example, we want to know step by step, if I change this voltage, not just 0.7, I'll give 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. If I keep on increasing the voltage step by step, how is that my current is going? Please, this is the electron direction. The actual direction, the current direction is always, the conventional direction is always in the opposite, right? So step by step, if I keep changing this voltage, VB, how my IC is going to change? How my IC is going to change? This is one relationship. The other relationship is step by step, if I change the current IB, how my IC is going to change? Next, will my IC change with this voltage, VC? As I keep on changing my VC, by changing the load, suppose I remove a bulb, put a small bulb, then a medium sized bulb, the bulb size of my head. So if I keep on changing different bulbs here, then my VC will change. When my VC changes, how my IC is changing. So this experimentally we want. So what is the relationship between IC and VC? What's the relationship between VB and IC? What's the relationship between IB and IC? And what's the relationship between VC and VB? When my VC changes, how my VB will change? If you know all the 4 different types of dynamics in the circuit, keeping other things as constant. When I'm doing with VB and IC, the other things like the VC has to be kept constant. If you know all these 4 combinations in your mind, then once you model it, that's it. We can just throw this dabba and we can have a new diagram for it, a new diagram which will explain exactly the actual behavior of a BJT, right? Initially, I have to tell you, Shockley has drawn this circuit for a 2-transistor bistable circuit, and he has published it in some newspaper, right? I think the Times or something. So Shockley has drawn 2-transistor circuits. For example, what is that? Any 2-transistor circuit that you know? Instead of drawing the whole bistable with resistors. Okay, suppose I have a Darlington pair, right? Now, when this symbol didn't come, they had these boxes, right? This is emitter, base, and collector. And then the emitter, base, and collector. Now you can see here, this is the emitter. The emitter of the first one is connected to the base. And both the collectors are shorted here, right? And the input is given here. Now, if I give you a diagram like this, you'll just keep on staring it. What if there is a differential amplifier with 6 transistors? So if you keep on thinking electron will go, there'll be a recombination, and then they get attracted towards positive. I mean, for 1 transistor, you might do that, but that explanation is not fit when you have to build circuits, right? Because this is not a device course. It's a design course. So you have an analog basically is the art of connecting these devices. So how you connect these devices will give them a new life. For example, I connected it like this. It's a Darlington pair. If you connect in some other fashion, it's a current mirror. If you connect in some other fashion, it's a differential amplifier. It's the same transistor, but the way how you connect them will give them a new name. Are you getting? But in order to get that, I mean, this explanation, this is not a good idea, right? So that is why then they said, drawing BJT is getting difficult, and we need 4 dynamics. What are the 4 dynamics? How VB changes with IC, how IB changes with IC, or rather how IC is going to change with IB, and how if there is a change in VC, how my IC will change. That is something called early effect, which I will discuss, and then how VC is going to change with VB. So to know all the four dynamics, then you can do AC analysis. This four dynamics is for AC analysis. For DC analysis is nothing there, just give 0.7, device is on. In DC analysis, there is nothing to do, right? You have to just check whether base emitter junction is forward bias or not. So if you just give 0.7, the device is on. That is DC. But AC analysis is very important when the four dynamics are important. Are you getting? So we'll go step by step. Let's understand what are the four different relationships for this circuit. So tell me which one is a better idea now? Which one is better? Not these boxes, but this symbol. This symbol is better. Are you getting? This arrow indicates this is emitter. This is base, collector. Emitter, base, and collector. Am I right? And this current is going to be IB. Here you have IC, right? And here there is VBE and VC. And see here how I have written here IB, VC, VB. So it's not good, right? Only dabba is there, emitter, base, and collector. So this is a much better way of drawing. So from now, tell me, what are the four relationships here? Keeping the other two things as constant, then we are doing something that is useful, right? Okay, so what are the four relationships? The first relation, of course, this we know, IC and IB. This is going to have a linear variation. A linear, whether you talk electron or hole or whatever it is, if you look at the currents between IB and IC, they both are going to have a linear relation. Linear relation. So what is the linear relation here? IC is given as beta times of IB. IC is given as beta times of IB. The current IB and IC are going to have a linear relation. Now what about the current IC and the VB? And the VB. This is nonlinear. This is nonlinear. And I already mentioned this, VB and IC. Your IC equal to some constant IS into e power VB by VT. VB by VT. A small change in voltage is going to create a large current. IC equal to IS into e power VB by VT. This is the relationship between the voltage applied at the input and the current drawn. What is the relationship between VB and VC? Now this relation, you can neglect it because the change is very, very small. Delta VC equal to point or delta VB we can write. Delta VB equal to 0.0001 times of delta VC. So what do you mean by that? If my VC changes by 1 volt, if my VC changes by 1 volt, right, suddenly from 5 volt to 6 volt, if it changes, then my VB is going to change by 0.0001 into 1, right? It's almost 10 power minus 4. In H parameters, this is called HRE. It's called HRE. So this term we can always neglect. You can always neglect this. You can always neglect. And what about the fourth one? The fourth one is called early effect. The fourth one is called the early effect. It is a relationship between IC and VC. It's a relationship between IC and VC. So what is this early effect? Now suppose I change the load. This is my load, RL or RC. I change this from 1K to 5K. 1K to 5K. And my IC is 1 milliampere. 1 milliampere. Right? RC, 1K, 2K, 3K, 4K, 5K. IC is almost 1 milliampere. Then what is my VC? My VC equal to this drop here equal to, it is 10 minus drop. When I say 10, it is a voltage here with respect to ground. So you can apply a loop here and you realize that VC equal to 10 minus IC into value RC. IC into RC. Now, if my RC is 1K, 10 minus 1 is 9, 10 minus 2 is 8, 7, 6, and 5. So now you can understand that the VC is changing from 5 volt to 9 volt. My VC is changing from 5 volt to 9 volt. So you can take a VC on x-axis and IC on y-axis. IC on y-axis. Now, ideally it should be like this, right? This is VC, is IC. If the characteristics is like this, if VC changes, if my IC is constant, this is some kind of an ideal behavior. Then what is the slope now? The slope is change of y by change of x. So what is the slope of a line parallel to x-axis? The slope of a line parallel to x-axis, which is delta IC by delta VC, is 0. Then what is the output resistance? The output resistance R0, which is 1 by slope, which is voltage change by current change. So now if you ask me, if VC changes, how IC will change, then your output resistance is infinite. It is 1 by slope. Slope is 0. So whenever I say the output resistance is infinite, I told you first class, it is called an ideal current source. The BJT is called an ideal current source, right? But practically, this does not happen. What happens practically? Practically, if VC changes from 5 volt to 9 volt, 5 volt to 9 volt, then my IC is going to change like this. It's going to change slightly more, right? Now, why is this happening? Why is this happening? Or there's another guy, there's a guy called, I think, Jim Early or something. Now, this man, Jim Early, he found a beautiful phenomena. The phenomena is, even if you try to draw, suppose this is for VB1, if you try to draw for different VBs, right? Say this is 0.71, there's 0.72, 0.73, like that. So if you take all these, you will get curves like this. But when you try to extrapolate them, Jim Early found that all these they meet at the same point. They meet at the same point. This is called the early voltage. After Mr. Early died, they started calling this, because if somebody is alive, they don't give names, right? So when you extrapolate them, they all meet at the same point. So early voltage. Early voltage. Now, this early voltage is given by the examiner, but why we are getting these characteristics we will discuss. So how are you going to calculate the output resistance from this graph? Suppose I want to calculate the output resistance of this one, right? I need a slope, because here we know that resistance means 1 by slope. So what is the slope of this portion? This is my VC, delta VC, and this is my delta IC. So how do you calculate the resistance there? How do you calculate resistance? So the resistance of the slope of this chota triangle is same as the slope of this bada triangle. Right? The slope of the big triangle here, so you can just draw a line here, right? Now this is your IC, this 0, this is your early voltage. Please don't get, this is in the negative axis, so I took mod. That mod will tell you my distance from 0 to this point. And here I'm having VC. So what is the slope of this triangle here? Slope is given as change of y by change of x, which is IC by VA plus VC. VA, you can see here, this IC here, and from here to here, this is 0, this VA plus VC. But do you know what is the magnitude of this VA? VA is much, much larger than VC. Suppose this is 200 volt, VC is going to be very small, right? So this is approximately IC by VA. This is a slope. Now what is R0? The output resistance, which tells you the relationship between VC and IC. So if somebody asks you how VC will change with IC, right? This one, how VC is going to change with IC. Here, how VC is going to change with IC. What you can say? VC changes with IC by this factor. What is that factor? The early voltage that is given in the data sheet, right? Or examiner will give this early voltage, a constant, 200 volt, 300 volt, or 50 volt. That voltage divided by the operating point, ICDC. So this is going to give you the dynamics between VC and IC. Now, why this line is coming like this? You know, why not the straight line parallel to x-axis? If you see, this is called what effect? Early effect. So what is early effect is, suppose if load changes, what is the load? From where it is changing? Load. If load is changing from 5K to 1K, if my load is changing from 5K to 1K, if load changes, right, then VC varies from where to where? In this case, VC varies from where to where? 5 volt to 9 volt. 5 volt to 9 volt. Now tell me in a BJT, Kirchhoff's law I will give you, but right now I need that voltage. This VB, suppose it is 0.7. This is VC. Here you have C. And this is VCB. This is what? VCB. So VC equal to the voltage from collector to emitter is collector to base plus base to emitter. So it is VCB plus 0.7. So if VC changes from 5 volt to 9 volt, then it means that VCB varies from from where to where? 5 minus 0.7, 4.3 volts to 9 volts. 4.3 volts to 9 volts. So if VCB changes from 4.3 volts to 9 volts, then what happens? Then what happens if load changes? The VC will change, which means VCB will change. Let me draw the diagram here. This is something called the base width modulation. It is something called base width modulation. Here, this is your RC. Here you have VCC, right? Here I'm having RC and VCC. Now for this, say VCB is 8.3 volt, right? Here VCB is 4.3, right? So here VC is 5 volt. So your VC is 5 volt means RC should be 5K. Yeah, this is 1K. This is 1K. So let me say what happens internally for these two cases. For these two cases. Now, this is emitter, base and collector. Here VCB is the voltage, is the reverse bias voltage between collector and base. Here VCB is going to be 8.3. What happens when you increase the reverse bias voltage in a PN diode? When you increase the reverse bias voltage in a PN diode, then it so happens that what will happen to the barrier now? The barrier is going to extend towards the base region here. Suppose this is, what change color? Now this is 4.3 volt, right? There's already a barrier here. Already barrier. So this is your base width. This is the base width. Now what happens if it is 8.3, right? This is 8.3. Then what will happen? It's going to extend like this. This is your base width now. Effective base width. So let me extend this. If load changes, VC will change. If VC changes, VCB will change. If VCB changes, if VCB increases, the effective base width will reduce. If the effective base width reduces, then the recombination will reduce. The recombination reduces. If the recombination reduces, then your IC is going to increase. So it's simple. I told you a simple analogy, right? Suppose if 100 soldiers have started their journey, and you have a VCB here, and say imagine 100 soldiers have started their journey and 5 people have died. Only 95 are reaching. What happens if your VC still increases? If your VC still increases, the base width will still reduce. So for recombination, this time 5 soldiers will not die, only 1 will die. So as your VC, so all this is happening by changing the bulb. So don't underestimate the bulb. If you keep on increasing the resistance of the bulb, what will happen if you keep on changing the resistance of the bulb? As load changes. So if somebody says, how are you going to have early effect? Simple, RC load. If RC keeps on changing from 1K to 5K, your VC is varying from 5 volt to 9 volt. The reverse bias voltage, VCB, is going to vary from where to where? 4.3 to 8.3, 4.3 to 8.3 volt. 4.3 to 8.3 volt. Then what happens if the reverse bias voltage changes? If VCB increases, the effective base width will reduce. So recombination is also going to change. So your IC is not going to be constant. Of course, any EDC book will teach you this. But what am I going to do in analog? What I'm going to do in analog is, even if you change the load, I will not allow VC to change. I'm going to show you current sources like the Cascode current source, Wilson's current source, where you change the load, VC will be fixed. Change the load, VC will be fixed. You change the load. So your VC will not change. When VC does not change, then your IC, there is no scope to change. So this is something we are going to do in future. But when you look at the device, every nonsense will be there in the device. When you study EDC, you realize that this device is utter useless, right? But in analog, we are going to tame that device. We are going to tame that device, and we are going to, finally make a very good amplifier from a very bad device, right? So that is the greatness of the design perspective. Device perspective, when you look at the device will have all problems, right? First, I told you the device is nonlinear. There'll be nonlinear distortion. So somehow what we did, instead of giving a big signal, we have given small signal. So somehow we were able to reduce. Then there is a problem with what? Load. Now you keep changing the load, VC will change. If VC changes, VCB will change. VCB changes, base width will change. Then current will also change. This is a big headache. So we have to think, how do I build a cascode current source with 2 transistor, 3 transistor? Somehow I should not allow that VC to change. If my VC remains constant, then my VCB will remain constant. If my VCB remains constant, then the recombination is same for any value of load. Then my IC is always going to be same. So that is, and VB is also a problem. Slowly I'll tell you, this VB will change by 2.5 millivolt for every 1 degree rise in temperature. So when VB changes, there is a tremendous increase in IC. So then how do I control that? I should say VB don't change. So when VB does not change, your IC will also. So all this we are going to do in future, right? That's the main aim of analog, right? So when we are building circuits, we have to know the what are the disadvantages with the device, right? At least you have to know the 4 relationships. Remember, what are the 4 relationships now between IC and IB? There is a linear relationship. Between IC and VB, there is a nonlinear relationship. When BJT is a unilateral device, right? There is no reverse transmission. So when VC changes, your VB does not change much, then it's okay. But early effect, you have to carefully observe, right? So the bulb is very, very important. The bulb is responsible for this early effect. The moment you keep changing the load, what happens the moment you keep changing the load? Your VC will change. If VC changes, then naturally what will change? VCB. If VCB changes, then your IC is also going to change. So please be very, very, you have to observe this, right? So how can I make my VCB constant, right? Yeah, I have to make my VCB constant. So this is emitter. This is base. So all these 4 relationships, we will repeat it again and again. Are you getting? Because when we are doing AC analysis, we need all these 4 relationships so that we understand the dynamics of the circuit, right? But before going for AC analysis, first we have to spend some time on DC analysis, right? And we have to check the region of operation. Okay, so how we are going to eliminate early effect, we will see later. But what is early effect? If load changes, VC will change. If VC changes, the reverse bias voltage VCB will also change. For different VCB, there is going to be different base width. For different VCB, different base width, the recombination is also going to be different. When the electrons from the N material, they go to P and they recombine, the recombination is different for different values of load. Then naturally your IC is also going to change. If the recombination, after recombination, if you can see here, where did I draw this? Yeah. So you can see as I keep on increasing my voltage, what is happening when VC is increasing? Why the IC is increasing here? Why this IC is increasing? For 9 volt of VC, there is an 8.3 volt of VCB. So you can see that the effective base width has reduced when your VCB has increased. You can see here when VCB has increased here from here to here, the reverse bias voltage, then the base is left with the base width is extremely small, right? The base width is going to be extremely small. But whereas here, from here to here, this 4.3, and then from here to here, it will be like 5. From here to here, it will be like 8.3. Are you getting? So when the voltage, reverse bias voltage increases, the barrier also will extend it into the base region. The effective base width will reduce. So the recombination is going to change, and naturally your IC is also going to change, right? This is something you have studied in your EDC course. It was okay. But in analog, what we are going to do is, even if you change the load, I will show you that the VC will not change. So we have to build circuits like that. And that's how we can eliminate the early effect, right? Okay. So keeping the 4 dynamics aside, first we should do DC analysis. That is more important. For that, let us go back here. The arrow indicates that this is emitter, base terminal, collector. So this is an NPN transistor, NPN. Am I right? Now between P and N, you can imagine that there is a diode. This is just an imagination. Don't think a transistor is 2 diodes connected back to back, right? This is wrong. This is just, you should imagine, right? There's a P material, there's an N material, there's a P and an N, right? Now when you have 2 diodes, you can have 4 combinations. You can have 4 combinations. So 2 junctions are there. One is emitter base junction. One is emitter base junction. The other one is collector base junction. Collector base junction, right? So this is the emitter base junction, and you have a collector base junction. 2 diodes are there, right? Now what happens if both the diodes are off, right? This emitter base junction, this reverse bias, this collector base junction is also reverse bias. What if both the diodes are reverse bias? Then the transistor, the current coming from the collector terminal is cut off. There's no flow of current from the collector terminal. So you can imagine here, I told you a bulb is there. Here we have a bulb. The bulb is this, and this 5 volt, right? What if I don't give any base voltage, right? I am not giving any voltage here. So this junction is reverse bias, no voltage. So this is ground, suppose. So between ground and ground, there is no voltage here. So this is reverse bias. And the collector base junction, there's a large positive voltage given here. Naturally, this is also reverse. So when no voltage is supplied at base terminal and the emitter is already grounded, naturally, when both diodes are reverse bias, the transistor is in what region? Cutoff. It is in cutoff. But for proper operation, what we have to do? I told you we have to clap, right? If you just clap, the transistor is working properly. So when you clap, what is happening? From the microphone and the rectifier, you're somehow supplying a 0.7 volts here. You're making base emitter junction as what bias? Forward. And collector base junction is reverse bias. See, why am I not talking about collector base junction? I'm just searching in the comment section again and again, right? Why am I only talking the forward bias, base emitter junction, electrons from the N material, they go to P and get attracted. I'm referring only this. Why am I not talking about the collector base junction, right? It's not needed. Why it is not needed that we have to discuss about the collector base junction? Why are we worried only whether the base emitter junction, only when this diode is on or not? So we are worried whether this diode is on or not. We are not worried about the other diode, right? So why? Think about it. Why we are worried mostly about that means the effort that you put on a diode is the same effort that you're putting on a BJT. We are least bothered about the other diode, the collector base junction diode. We are only bothered about the base emitter junction. Why is this so? So in active region, base emitter junction is forward, collector base junction is reverse. So what happens when both the junctions are forward? When both the junctions are forward bias, then BJT is in what region? Saturation. And what is the last combination we are left with? The last combination is, what if base emitter junction is reverse, but collector base junction is forward? This is inverse active. It is inverse active or reverse active. So this is a useless region for analog, because here you can build attenuators. So BJT is going to become an attenuator. What is attenuator? Decreasing the strength of a signal. What is cutoff? Cutoff means it's a controlled off switch. BJT is going to behave as a controlled off switch here. For active region, it is going to behave as an amplifier here. Amplification you can get. Of course, you have to give a signal at that operating point. Just because the base emitter junction is forward, collector base junction is reverse, no amplification will come. Some signal you have to apply at the operating point and change the dynamics. So all the amplifiers, voltage amplifier, current amplifier, transconductance, transresistance, RF amplifier, IF amplifier, video amplifier, instrumentation amplifier, all the amplifiers, BJT should be in what region? Active. In saturation, when both junctions are forward, it is a controlled on switch. On switch. So BJT has only three useful regions. Cutoff and saturation for digital logic, for digital on off, right? And active region is for amplifiers. Active region is for amplifiers, right? Yeah, tell me why I'm not bothered about the collector base junction, reverse bias. I'm just referring to base emitter junction. You switch on, the device is ready. See here, just tell me logic, simple logic. Suppose if I have 3 resistors, right? Resistors. And same example I've given many times. And I'm giving 15 volt here. I'm giving 15 volt. Say this is 5K, 5K, 5K. 5K, 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 right? Then what is the current I? I equal to 15 by 15K. It is 1 milliampere. So this voltage is going to be 5, 1 milli into 5. 1 milli into 10 is going to be 10. Now, between 5 and 15, you have got 10. That is okay. But can it ever possible that between 5 and 15, I get 2? I get 2 volt or I get minus 25 volt. Is it possible? It's not possible, right? When it's not possible, it is the VCC and the circuit that is going to take care of that, the reverse bias junction. You don't have to worry because I'm going to remove that 5K here. I'm just going to remove that 5K. And I'm telling you what happens if I put a BJT here. If I put a BJT, suppose this is some voltage, X volts, right? So suppose this is 3 volt. This is 3, this is 15, say this is 3.7. What happens if this guy is something like 9 volt here? Automatically this junction will be what bias? That junction is always reverse bias. See, the day you connect, the day you draw a transistor like this, finished. And the moment you connect this to ground and this to VCC, finished. The base emitter junction only you have to be bothered. The collector base junction, the device will take care. So similarly, I'll show you for a NPN transistor, for a PNP transistor, you should draw a symbol like this. If you draw a symbol like this, and if you connect one end to ground and the other end, as you go up, all the voltages should be in increasing order. Naturally, the collector base junction is going to get reverse bias. So if you want the collector base junction to get reverse bias, what you have to do? The emitter here is connected to ground or negative. Collector is connected to positive. Finished. Then your focus, your mind is going to focus only on one diode. What is that diode? Base emitter junction. The moment it is on, mostly see here, if this is 5, this guy is 10. Or this guy might be, what happens if I decrease this resistor? Tell me. If I keep on decreasing this resistor, what will happen? Suppose that 5K, I make it 4K, I make it 3K, I make it 2K. What is going to happen? The worst thing that is going to happen is this might become a short and this voltage will appear here. That is saturation. In saturation, what is going to happen is this voltage is almost equal to this voltage. Are you getting? But remember, never think that this diode is going to get on because this voltage will be less than this. No, it will never happen. It can never happen that this is 3. Can it ever happen that instead of 9 it is -2? -2, or instead of 9 it is 1 volt? Can it ever happen? I'll be a fool if I say that between 3 and 15 there is 1. But if it is 1, this diode will get what you call forward, but that will never happen. Are you getting? So when in saturation, what is going to happen is, in saturation, the same potential is going to appear here. The same potential is going to appear. If this is X, this is going to be X. If there is a BJT, this is X plus 0.7. And this junction is going to get forward. This junction is going to get forward. When the same potential appears here, this junction is going to get forward. Are you getting? So please, I repeat, finally see here, what is going to happen finally is, when we take up a problem, please observe Okay, can you hear me? Can you hear me? So there's no internet problem actually. The cable got disturbed suddenly. I'm using an Ethernet cable directly and the cable got disturbed. Okay, somebody did stamp, fine. Yeah, what I wanted to tell you is just look for the base to emitter junction and see the design where one end is connected to ground, the other is connected to VCC. The design is going to take care of the other junction. The other junction is always going to be reverse bias. Are you getting? So yeah, I was trying to tell you an analogy. What is the analogy? You give a base voltage, there's a big gap between emitter voltage and collector voltage. Increase it, the gap reduces. Still increase, gap reduces. Still increase, gap reduces. At some voltage, it's almost short or 0.2 volts. Still, if you increase, what will happen? How Kirchhoff's law will be satisfied? If you still increase, the extra current will keep on sinking through the base region. That is saturation. In saturation, I'll tell you what is happening in saturation is, in saturation, your IB in saturation, your IB is going to be greater than IC by beta. IC by beta. So please, only in active region, your IC equal to beta IB is valid. IC is beta IB is valid only in what region? Active. So because when you keep on increasing, the gap will reduce, and at some point of time it reduces to zero. You still increase, the extra current will keep sinking through the base region, right? So this, while solving small chota problems today, we will realize that this is the extra phenomenon. I mean, why is it happening? To satisfy Kirchhoff's law, that's it, right? You keep on increasing, but the voltage here is fixed at 0.2. The extra current has to sink through the base region, right? So we will see that. Okay, yeah. How do you apply Kirchhoff's laws? How do you apply Kirchhoff's laws for DC? First of all, transistors, there are two types. One is NPN and the other one is PNP. The other one is PNP. Now, how to draw an NPN? This is an NPN transistor, right? How do you draw a PNP? This is a PNP transistor. This is a PNP. This is an NPN. And I told you we have to worry only about this junction. This junction should be forward. The circuit will take care. Similarly, this junction should be forward. So if you give some positive voltage here, the device is going to get on. And don't worry about this junction. This junction, don't worry, because here we are going to give a positive voltage. Automatically it is going to get what bias? Reverse bias. And don't worry about this junction here, because here we are going to give 0 and this to positive supply. So automatically this junction is going to get reverse bias. So our main interest is now which junction? Only the forward bias junction, right? Okay. Now, how do you apply KCL? KCL, Kirchhoff's current law. KCL. Just look at the arrow here. All the equations for NPN are same for PNP. All the equations for NMOS are same for PMOS. So you can see here, the arrow here indicates that this is the emitter current. Am I right? It is what current? Emitter current, right? And this is leaving current or entering current. This is leaving, right? Because this is leaving, the other two currents should be entering. Because that is what Kirchhoff's law is. What is Kirchhoff's law? The current leaving should always be equal to the current entering. But what happens in a PNP? In a PNP, this is a PNP transistor. In a PNP, you can see that there is a current entering. The arrow indicates emitter, right? So this is emitter. You have base and you have collector. Now this current is entering. So entering current should be equal to the leaving current. Leaving current. You have to take IB and IC. Entering current equal to leaving. Now tell me what is KCL? KCL tells that the current that is entering is equal to the current that is leaving. I'm telling you, if you know how to write this, that's it. You can do DC analysis. All the DC analysis problems you can do, provided you know how to take the currents, right? So simple, look for the arrow. The arrow says that this is the emitter terminal. So the arrow indicates that this is an outgoing current. Then the other two currents are entering, right? So here this is entering. So the other two currents should be leaving, because entering current equal to leaving current. This is KCL. How will you write KVL? How will you write KVL? Now just tell me, how will you write KVL for, suppose I have a voltage, say V or VCC, and I have two resistors, right? If you know how to write KVL for this, then you know how to write KVL for the transistor also, right? Okay. Now, one end is connected to ground, the other end is, say, positive. Current is flowing in this fashion. What is the polarities? No device has polarities. Polarities will come only with the direction of current. So you have to take plus minus, plus minus, plus minus like this. Are you getting? So same thing with BJT. With BJT, see here, this is collector, this is emitter, this is base. So if this node is A, this node is B, and if A is plus, B is minus, what should I write here? Can I write VAB or VBA? What should I write here? I have to write VAB. Why should I write VAB? Because A is plus and B is minus. Now you tell me, please see the current directions here. Please see the current direction. Plus, minus, blindly, right? So here also plus, minus, like this you can write. So is there any difference? No. If you know how to write for a resistor, you know how to write for a transistor. And what is that we have to write? Here, the voltage is between collector and emitter. Voltage between collector and emitter, you can write VC, right? The voltage is between collector and base, you can write VCB. Here it is between base and emitter, you can write VB. And the good news is, you can go clockwise or you can go anti-clockwise. Your answer is not going to change, right? So you can go clockwise. What do you get? Minus VB, minus VCB, plus VC equal to 0, or VC equal to VCB plus VB. VC equal to VCB plus VB, right? Any problem here? No. Now, I will not say anything. You tell me, how will you write for a PNP? It's not, because if you know how to write for resistor, you know how to write for transistor, MOSFET, everything, right? So this is E, this is B, and this is C. Here one end is ground, other end is positive. So what are the polarities now we are going to take for resistor? Plus minus here, plus minus here, right? So for this also, plus minus, plus minus, plus minus. Am I right? Now tell me, what are the voltages that you're going to write here? Tell me. This voltage is between E and C. So what should I write here? VEC. What should I write here? VEB. What should I write here? VBC. You can go clockwise or you can go anti-clockwise. So if you go clockwise, minus VBC minus VEB plus VEC equal to 0. So your VEC equal to VBC plus VEB. Now please observe the equation of NPN with PNP here, NPN with PNP. Did you find any difference? Any problem with KCL? Any problem with KCL? IE is IC, very, very important. IE is IC plus IB. Any problem with KVL? Plus minus, plus minus, plus minus. Plus is taken as, if suppose this is A, this is B, you have to write VAB. What is the relationship between VAB and VBA? Yeah, I have to write that. I forgot. VBA is always equal to minus of VAB. Am I right? VBA is always equal to minus of VAB. Now, can I write VCE as minus VEC? Can I write VCE as minus VEC? VCB as minus VBC? VB as minus VEB? If you cancel minus at the left side and minus at the right side, that is what you get here. So, PNP transistor and NPN transistor, both equations are same. Instead of VEC, you can write VC minus VC, minus VCB, minus VB, minus VBC, and minus VEC. Are you getting? So if you write with a negative sign, what is going to happen? What is this annotations? Spotlight. Oh. See, can you see my cursor actually here, right? There's something called annotations and spotlight here. Maybe I can use some light or something. Okay, anyways. Can you see this cursor, right? Yeah, the VCE, you can write it as minus VEC, minus VBC, minus VEB, right? Then the NPN equations and PNP equations, both KVL and KCL are same, right? See, otherwise, let me tell you, suppose, can you see my cell phone, right? Can you see my cell phone here? Or just imagine this is a book, right? So this is a book now. I'm reading the book like this, right? So this is a book. Now, I have some circuit on the book. And now what I'm doing is, the same circuit, I'm seeing like this. See, I'm not changing the, what you call, I'm not changing any diagram in the circuit, but I'm looking like this. There's the other guy who looks like this, right? So an NPN and PNP are like that, right? We are not going to change anything. It's emitter is emitter, base is base, collector is collector. But here emitter is down and the collector is up. But here the collector is down and emitter is up. So if the examiner has given you a PNP, just draw an NPN transistor here. Whatever connections that you have given here, the same if you draw here, your answer is not going to change. The small signal analysis of the small signal model of NPN and the small signal model of PNP, both are absolutely same. Both are same. Are you getting? So it's same thing. See here, KVL is same, KCL is same. What more do you need? Voltage is same, currents are same. So your answers of NPN and PNP, both are going to be same. Of course, I spend equal time for both NPN and PNP, right? But what I'm trying to tell you is, even if the examiner gives you a PNP transistor, common emitter amplifier, you can convert it into an NPN, your answer is not going to change, right? So KVL, KCL, finally, before I take up simple problems on this, finally, tell me, how will you check for active region? Active region, I have a NPN transistor and a PNP. When do you say that a device is on? When do you say that a device is on? The first step is, the base emitter junction should be what bias? Forward. For all our problems, I will take 0.7. Are you getting, right? Consider VB on 0.7. And consider IC is beta IB. IC is beta IB. Your VB on is 0.7, right? Consider Consider. And what is that you have to prove? There is nothing to prove. As you go up, the voltages should be in increasing order. If they are increasing order, this junction will automatically be what bias? Reverse. So for this to be reverse bias, who should be at higher potential and who should be at lower potential? Simple. If you prove collector voltage is greater than emitter, that is enough. If you prove VC is greater than VE, then BJT is in active region. Now you might say, sir, what is there? Always when you draw any diagram, the upper one will be at higher potential, lower one will be at lower potential. Obviously, if the upper, so that means it needs simple logic. If collector is greater than the emitter, then the BJT is in what region? Active. Similarly, here, this is the emitter, this is the base, and here there is a diode. So you have to consider VEB on 0.7, IC is beta IB. IC is beta IB. Prove, what is that we have to prove? As I go up, the voltages should be in increasing order. So who is at a higher potential and who is at a lower potential? Your VE is greater than VC. If you prove VE is greater than VC, then the BJT is in what region? Active, right? BJT in active region. BJT in active region, right? So for saturation, your IB should be greater than IC by beta, or your beta forced is less than beta active, right? There should be a huge base current flowing. Yeah, how will you check for saturation? Once again, I will tell you, for all the problems of saturation, when the gap reduces to 0, I will take 0.2 here. Yeah, some gate problems it is 0, some gate problems it is 0.1. Textbooks they take 0.2. Some gate problems it is 0.2. So this is collector, emitter, base. So what we have to consider? Consider VB on 0.7. Consider VC equal to 0.2 in saturation. What is that you have to prove? You have to prove that the IB is much greater than IC by beta, or beta forced is less than beta active. That means beta active means the device beta. Beta active means device beta. The circuit beta, which is the ratio between IC by IB, that is going to be less. So tell me, when beta is less, what are the two things that can happen? Less beta. Beta is nothing but what? IC by IB. So IC by IB is beta. When I say beta is reducing, what do you mean by that? Either IB has increased or IC has what? Reduced. In what region? Saturation. In saturation, your IB has increased or IC is reduced. That means the beta forced is less than the beta active, the device beta. This is the device beta. Right? Oh, I've not done for PNP. For PNP, emitter, collector, base. Here, this device should be on with 0.7. Here there is 0.2. 0.2. So what we have to consider? Consider VEB on 0.7, VEC SAT, which is 0.2, and prove that your beta forced is less than beta active. Same thing. Or you can say IB is greater than, or IB is greater than IC by beta. IB is greater than IC by beta. It's one and the same. So this is the condition for saturation. Right? So what do you mean by beta forced? Forced means intentionally we are making the IB to increase and the IC to decrease by giving a large base voltage or by increasing the collector resistor. I will show you by increasing. So that means we are, see, it is like the op amp. In op amp, when the op amp gain of 10 lakhs is 10 lakhs, and when the gain of 10 lakhs will reduce, tell me. Yeah, this is a simple analogy. In op amp, an op amp that is saturated and the op amp that is active, right? That is inactive. What is the difference? Tell me. If an op amp, it is in saturation, then the non-inverting V1 is suppose greater than V2. Here, V1 will be equal to V2, right? If V1 is greater than V2, suppose this is 3 volt, this is 1 volt, this is 1 volt. What is the difference? 2. Suppose output is saturated at 12 volt. Then what is the gain of this op amp in saturation? Gain is going to be gain forced. This forced gain is 12 output by 3 minus 1. What is 3 minus 1? 3 minus 1 is 2. 12 by 2, 6. See, no fool will design an op amp with 6 gain. Why the op amp is showing 6 gain? Because it is saturated. When it is saturated, in a BJT, the base current will increase. Here, VD will increase. Here, VD increases. In BJT, what will happen in BJT? Your base current will increase, and the beta value, then it's going to be, it's fall. It is going to fall. Suppose beta is 100. Now I'll show you in problem, the beta value will fall down to 1 or 0.5, 0.05. So it's not at all a BJT. That means the device BJT is good, but the network is forcing a new value of base current, a large value of base current, and a small value of collector current. Thereby, the device has saturated. Are you getting? So in saturation, but what is happening in active region? In active region, if suppose this is 6 volt, there will be 6 micro difference between the two. Your V1 is almost equal to V2. Are you getting 6 micro? The VD is almost 0. The VD is almost 0. So now you tell me, when is a BJT an ideal BJT? An ideal BJT is one whose IB is almost 0. Whose IB should be 0. If IB is 0, then your IE and IC, no soldier will die here. Your IB, your IE and IC are same. Then ideally, beta ideal is going to be infinite. What is AOL ideal? AOL, the open loop gain ideal, is also going to be infinite in op amp. Are you getting? Right? So the error between the two terminals at the input should be as small as possible. So even in BJT, if your base current is small, then it is ideal. What happens if base current increases? Finished. If VD increases, the device gain is going to fall. If IB increases, then the device beta is going to fall. So what is beta called? What is beta and what is AOL? AOL is open loop gain. Open loop gain. Open loop gain, right? Or open circuit voltage gain. It is also called the open circuit voltage gain, right? This is AOL. Beta is short circuit current gain. Beta is called short circuit current gain. It is called what gain? Short circuit current. Strictly, it is IC by IB when the VC is fixed. then the VC does not change and VC is constant. Constant means what? Delta VC is 0. So IC by IB is beta, right? Here it is V naught by VD is open loop gain. So I'm just giving you what it means by saturation, right? So when is a device dead? A device is dead when the gain, circuit gain, will reduce the actual gain of the device. The device gain is very high, circuit gain is very less. That's called the forced gain. Are you getting? So VC 0.2 is given by the examiner. Are you getting? So I'm not writing. It should be 0. Ideally, it should be 0 when it is saturated. There is a short. Okay. Yeah, one last thing I forgot to tell you. What is the relationship between emitter current and collector current? This is very important. IC is beta IB and IE is IC plus IB. That means it is beta IB plus IB is IE. So your IE is beta plus 1 times of IB. Very, very important. Very important. Your IC is beta IB. Your IE is beta by your IE is beta plus 1 times of IB. Then what is IC by IB? What happens if you divide these two? It is beta by beta plus 1. It is beta by beta. Very, very important. This you can call it alpha also, right? But it's very, very important relations, right? IC is beta IB, IE is beta plus 1 IB, IC by IE is beta by beta plus 1, right? Beta by beta plus 1. If the examiner says beta large, what do you mean by beta large? Beta large means what? IC by IE is beta by beta plus 1. If the examiner says beta large or say beta infinite, it is 1 by 1 plus 1 by beta. If beta is infinite, that means your IC is, your IE is equal to IC. That is means by beta large, right? That means that your IB is neglected. IB is very, very small. Small IB is flying. So beta large means good BJT, right? A good BJT should have collector current equal to emitter current. Its base current should be as small as possible. Very, very important relation. These three are very important relations. Okay. So one simple problem we will do. Calculate all the node voltages and branch currents. Calculate all the node voltages and branch currents. For all the problems, we will take beta 100. If I say beta infinite, it's okay. If I don't mention beta, just take beta 100, right? You don't have to tell me, sir, I'm taking beta, what should I take? Take 100, right? Beta equal to 100. VB on equal to 0.7. VB on equal to 0.7 volts. calculate all the node voltages and branch currents. Now, all of you, before I calculate this, I want you to follow a procedure. What is the procedure is? First, you have to find emitter voltage. Please see here, VE. Then you have to your first step, you have to find VE. Second step, you have to find IE. Third step, you have to find IC. Fourth step, you have to find VC. Please. So whoever, right, sitting before the system, please repeat in your mind. What you should repeat in your mind? VE, IE, IC, and VC. VE, IE, IC, VC. Are you getting? Say it 5 times. Say it 5 times in your mind, right? VE, IE, IC, VC. VE, IE, IC, VC. Now see how simple BJT is going to look, right? Step 1. VE. VE. Now I told you there is a diode here. There is a diode, and diode takes a drop of how much? 0.7. 0.7. So yesterday also we have done problems that if you come down, you have to subtract. If you go up, you have to add. Are you getting? So this is 4. What is VE? It is 4 minus 0.7. It is going to be 3.3 volt. First step is over. 4 minus 0.7. So suppose if VE is 4, what is VB? If you go up, you have to add. If VE is 4, your VB is going to be 4.7. But now I have given VB 4, your VE is going to be, you're coming down, so you have to subtract 3.3. So first step is over. What is step 2? Step 2 is IE. After VE, you have to go for IE. See what is IE here? VE minus 0 by 3.3K. It is VE minus 0 by 3.3K. It is 3.3 by 3.3K, 1 milliampere. Your IE is going to be how much? 1 milliampere. Am I right? Now, step 3. Step 3. What is IC? What is IC? Just now, I have given you a relationship. What is the relationship? IC by IE. IC is small, IE is large. IC by IE is beta by beta plus 1. You remember? Beta by beta plus 1. IC by IE is beta by beta plus 1. So it is 100 by 101 times of 1 milli. It is going to be 0.99 milliampere. Over. Last step. If you do that, your BJT problem is done. This is the reason BJT problems are much simpler than diode problems. Why? Because they provide isolation. Suppose if 2 diodes are there, we have seen how much struggle we have to do. But here, even if 5 transistors are there, you can very comfortably do because BJT provides isolation. What is step 4? Step 4 says that what is VC? What is VC here? What is IC here? IC here is going to be, what is IC? IC is going to be 10 minus VC by 4.7K. Am I right? So what is VC? What is VC? You can apply logic. What is the logic is? This voltage will always be less than 10. This voltage, because you're coming down, it should be always less than 10 by a drop IC into 4.7. So it is going to be 10 minus IC into 4.7. 1 milli into this, it is 5.3 volt. 5 point. Okay. So what are the steps? I repeat: VE, IE, IC, VC. Repeat: VE, IE, IC, VC. All of you tell this orally. Orally, you tell me. All of you. Once again, I am writing. Orally, you have to tell me. Are you getting 4, 3.3 K, 4.7 K, 10 volts? Tell me orally again. We'll do this a simple practice. Are you getting? Yeah, tell me 4. First V. 4 minus 0.7. How much? 3.3. 3.3 by 3.3 K, 1 milli. If this is 1 milli, this current IC is also 1 milli, right? 10 minus 1 milli into 4.7, 5.3. Are you getting? So what is first step? 3.3, 1 milli, 1 milli, 5.3. 3.3, 1 milli, 1 milli, 5.3. Are you getting? So tell me, if this is 4, there's a drop of 0.7. What will you write directly here? 3.3 volt. You have to write. This is first step. What is second step here? 3.3 by 3.3 K, it is going to be 1 milli. This is 1 milli. This is also going to be 1 milli. Then what is this step? 10 minus drop. So 10 minus 4.7 is 5 point. Are you getting? So can't you do it orally? Yes or no? Now tell me, what is a check we can do? What is a check we can do now? Check. As I go up, the voltages should be in increasing order, I told you. This is 3.3 volt. This is 4 volt. This is 5.3. Now, do I have to check this diode? Do I have to check this diode? 5.3 at cathode, 4 volt at anode. Automatically, this diode is reverse bias. Of course, this diode is forward bias. The BJT is in what region? Active. So I told you there is no need for you to do it because is your collector greater than the emitter voltage? True. Therefore, BJT is in what region? Active. Therefore, BJT is in what region? Active region. Okay. So it is 0.99. That means it should be 5.31, something like that. Are you getting? So approximately this is 1 milli. So BJT is in active region. Are you getting? So is it difficult to do? 4, 3.3, 1 milli, 1 milli, 5.3. Are you getting? All of you, just tell me a second example here, orally. 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 Yeah. I'll give 1.7 volts for your simplicity. Just tell me, what are the voltages now? What are the voltages? All of you, in your mind, tell me. First step, VE. What is VE? What should I write VE here? There is 0.7. 1.7 minus 0.7. How much? 1 volt. Are you getting? What is the current here? IE. What is IE? 1 by 1K. How much? 1 milli. If this is 1 milli, this is 0.99, almost 1 milli. Then what is this voltage? 10 minus 3, 7. Is it difficult now? Huh? BJT, see how simple BJT is. Are you getting 1.7, 1 volt? The current is 1 milli. This is also 1 milli. 10 minus 1 is 7. So is 7 greater than 1? Is your VC greater than VE? VC greater than VE? True. True. So BJT in what region? Active. Yes or no? Just as an example, like this, you can create so many examples. You can give 2 volt, you can give 5 volt like that, and you can do it. Are you getting? See when you are violating it, right? At some point, it is going to violate. We will come to that. Are you getting 1.7? 1. Is it difficult? 1.7 minus 0.7. 1. 1 by 1K, it is 1 milliampere. Are you getting? 1 milli. This is also going to be 1 milli. 10 minus 3 is going to be how much? 7 volt. Are you getting? Right? Yes or no? Right? So like that, you can create so many examples. Example 3, if you want, you can do it orally, or you can do step 1, step 2, like that, right? Okay, all of you, are you ready? Are you ready to do it orally, or we'll do it step by step? I mean, either way. I mean, after this, we'll take a break. I think it's 7. So just tell me orally, this is 0, right? If just tell me, if I have some voltage X here, if I come down, this voltage should be X minus 0.7. Am I right? So this is 0. I'm coming down. Cathode is given to -5. So definitely this guy is on. This guy is on here. But what is VE here? VE, first step. So if anode is at X, your cathode should be X minus 0.7. What if your X is 0? Then this is going to be minus 0.7, right? So VE minus 0.7, first step. What is second step? IE. IE. What is IE? IE is going to be minus 0.7. If you can do it orally, it's okay. Minus 5 by 4.3 K. So this is going to be how much? Same 1 milli. Are you getting 1 milli? If this is 1 milli, this current is also how much? 1 milli. And what is the last step VC? What is the last step VC? 12 minus that drop, it's going to be 11 volt. Just tell me, is 11 greater than minus 0.7? Is your VC greater than VE? True. That means BJT is in what region? Active. Are you getting? So please, before we take a break, just repeat in your mind, what are the steps that we are going to follow? VE, IE, IC, VC. VE, IE, IC, VC. Right? So let's take a break now. When we come back, we will have more fun with BJT. And let me repeatedly tell you, BJT is much simpler than diode problems. And what is the toughest topic in analog? The toughest topic in analog is diodes. The most toughest topic in analog is diodes. Are you getting right? The switch, that will create a problem. All MOSFET and BJT, they are much easier because they provide isolation, right? Any number of stages is very easy to do. Okay, so your collector is 11 volt, your emitter is at minus 0.7. Collector is greater than emitter. This junction is what bias? Reverse bias. BJT is definitely in what region? Active. So we'll take a break now. When we come back, we will see more of this. Okay. So remember the procedure that I told you: VE, IE, IC, VC. Is it not? So that is by Ohm's law. By using Ohm's law. I mean, if you don't like that method, you can follow the conventional KVL method also, right? Both are good. I will follow both the methods. Both the methods I'm going to follow, right? If it is KVL, the same problem. Repeat using KVL. Repeat the same problem using KVL. Repeat the same problem using KVL, right? So how are we going to do with KVL? Whenever I say there's a voltage here, it is a voltage at that point with respect to ground. This is 4 volt. So the +4 is connected to base terminal. +4 is connected to the base terminal. Ammeter is grounded, 3.3 K. There is 0.7 volts here. The collector is connected to 4.7 K. And here you have 10 volts, +10. Whenever I say +10, the minus is connected to ground. So you can solve the same problem using KVL also. So here you have IE, this is IC, there is VC. All right. Now you can write KVL. We're just going to repeat the same problem using KVL. So you can write -4 plus 0.7 plus IE into 3.3 K. This is current always flows from higher to lower. Whichever the sign that comes first, you can write. Minus comes first, -4, plus comes plus 0.7 plus IE into 3.3 K equal to 0. So what is KVL at the output loop? -10 plus IC into 4.7 K plus VC plus IE into 3.3 K equal to 0. Now from the first equation, we can get IE, right? You can substitute here, but there are two unknowns here, IC and VC. So what is the relationship between IC and IE? IC by IE is beta by beta plus 1. So it is 100 by 101. So when you solve here, I mean from the first equation, you get IE and then substitute IC by IE is 100 by 101, then you will get VC. Are you getting? This is by Kirchhoff's voltage law. I'll do both, right? KVL as well as Ohm's law. But Ohm's law says directly that if there is a 4 volt here, this node is going to be 3.3. Am I right? Because you are coming down by 0.7. This is 3.3, and this is V 3.3. Then IE is going to be 1 milli. Your IC is going to be 1 milli, and your VC is going to be 10 minus 0.99 into 4.7. That's around 5.3 volts, 5.32 something, and this is your VC. So if your VC is positive, if VC is positive, then VC is greater than V. VC is greater than V, BJT in active region. So as you go up, the voltages should be in increasing order. So BJT is in what region? Active, right? So we will do both, right? KVL as well as Ohm's law. Whichever you find convenient, you can follow. Okay, can you hear me? Can you hear me now? Is my voice clear? Is my voice clear? Yeah. Similarly, check the region, same beta equal to 100, VB on 0.7. You have to check the region of operation, right? In which region BJT is working. So let me take the same circuit and instead of 4 volt, you give 6 volt and carry on the same procedure. Do it with 6 volts and see if the BJT is still in active region or not. Check the region of operation. What happens if the 4 volt is changed to 6 volt? Okay, step 1, V. So here there is 0.7 volts diode. 6 minus 0.7 is 5.3. 6 minus 0.7, it is 5.3. Step 1. Step 2, IE. IE equal to VE by 3.3K. 5.3 by 3.3K. So what is 5.3? Calculators, 5.3 by 3.3K. Around 1.6 milliampere. Step 3, IC. IC is beta by beta plus 1 times of I. I told you in all the problems we'll take beta 100. If I mention, unless and until I mention, right? Otherwise you can take beta 100. 100 by 101 times 1.6 milli So this is around 1.58, right? Around 58, 1.6. So this is around 1.58 or 59 milli. And what is the last step for? VC is going to be 10 minus IC into 4.7 K. So this is around 2.52 volt. Now, is it a correct way of analysis? Is it a correct way of analysis? Is it true that between 5 volt, this is around 5.3, between 5 volt and 10 volt, what are the voltages that you can expect here? Tell me. Right? My daughter will say that this is wrong. Right? The reason is, if I ask her, what are the volt numbers between 5 and 10? She might say 6 or 7 or 8 or 9 or 10, but definitely she'll not say 2 volt, right? Now, between 5 and 10, can you get 2? No. So this makes no sense, no physical sense. So if you conduct this experiment anywhere in the world, right, in any lab, you will never get 2 volt between 5 and 10. You will never get 2 volt between 5 and 10. So what do you mean by that? It means that the analysis is wrong. BJT is not in active region. BJT is not in active region. If he is not in active, where is he? He is in saturation. He is in what region? Saturation. We will have to check. Are you getting? Check the region. For your convenience, I'm giving beta 100, right, in this problem. All the problems I'm going to take beta 100. What is VB on? 0.7. And what is VC? VC sat. In all the problems, if it is saturation assumption, you can take 0.2 volts. Are you getting? Right? So does it make any sense that between 5 volt and 10 volt, you're going to get 2.5? Does it make any sense? No, it makes no physical sense. It makes no physical sense. So BJT is not in active region. BJT is not in active region. So what happens when you supply that 0.7 volts? We expect that the electrons from the N material, they reach the P region, they recombine, and then get attracted towards the 10 volt supply. So the electron direction, you can see that it is like this. Am I right? But the conventional current direction is from is in the opposite, right? Because you know what you mean by convention. In those days, they thought that current always flows from plus to ground, plus to minus. So the same convention we are following, right? And later they realized that the electron is responsible for the flow of current. It's always in the opposite, right? Okay. Now let us check for what region? Saturation. Let us check for saturation. So in saturation, tell me, how did we do diode problems? In diode problems, if you assume voltage, then your findings are current. If you assume current, then your findings are voltage. Are you getting? If you assume voltage 0, then you have to find current ID. If you assume current 0, then you have to find the applied voltage across the diode. Similarly, if your assumption is IC equal to beta ID, current, then you have to find VC, whether collector is greater than the emitter. If as you go up, the voltages are in increasing order, BJT is in saturation, active. But if your assumption is not IC is beta, if your assumption is not current, it is voltage here. Can you see the voltage here? 0.2. And here how much? 0.7. Here there is 6 volt. If your assumption is voltages, then your findings are current. You have to prove that beta forced is less than beta active, or your IB is greater than IC by beta. So let's see. If this is 6, how much is this? 6 minus 0.7. How much? 5.3. And the worst thing that can happen is you cannot get 2.5 volt. Are you getting? You as the two voltages converge to 0.2, maximum you might get. This is 5.3. If you go up 5.3 plus 0.2, how much is 5.3 plus 0.2? 5.5 volt. So here there is 4.7K, 3.3K. This is IE. You have IC. And of course, there is IB. Now calculate the currents individually. Calculate the currents individually. Calculate the currents individually. What is IC? This 10 volt. IC is 10 minus 5.5 by 4.7K. What is IE? IE is 5.3 by 3.3K. Of course, this we have already calculated as 1.6 milliamp. What is IC? 10 minus, calculators, 10 minus 5.5 by 4.7. How much is this? 10 minus 5.5 by 4.7. How much? Thank you. They are saying it is 0.95 milliampere. Thank you. Good. Then what is the base current IB? It is IE minus IC. It is IE minus IC. So IE is 1.6 minus 0.95. I think I don't need a calculator for this. It is 0.65 milliampere. It is going to be 0.65 milliampere. Am I right? Now tell me, what is beta forced? Beta forced is IC by IB. 0.95 milli by 0.65 milli. 0.95 milli. See, beta is not even 2. It is around 6 ones are 6, around 1.4. Beta is around 1.4. Now tell me, what is circuit beta that I have given? What is the circuit beta that I have given in the problem? I gave beta equal to how much? 100. So beta 100 was true. Beta 100 was true when you gave 4 volt there, right? When you give 4 volt at the base terminal, beta 100 was true. Your collector is greater than the emitter. BJT is in active region. IC equal to beta IB is valid. But when you increase it to 6 volt, finish. The base current has increased, not in microamps. See, it's not in microamps, it is in milliamps. 0.65. Big, large base current is flowing. Beta is 1.4. So your beta forced is less than beta active. Less than beta active. Therefore, BJT is in what region? Saturation. BJT is in saturation. And please, all of you, you have to know that the answer that we got before is wrong. It's all wrong. It's all wrong because the BJT is not inactive. These are the correct numbers, right? So finally, we got the correct numbers. This is exactly the value of base current. Are you getting? So if the examiner asks you calculate IB, IC and IE, these are the correct numbers. What we got before, the BJT was not in active, it was in saturation. It is in saturation. So in saturation, what is happening to the value of beta? The beta value has increased or decreased? It is decreased, right? Beta decreased means your base current has increased, right? So now we have to carefully look at that base node. You have to carefully look at that base node because so what is the note here? Look carefully the base potential, right? Base potential to stay in what region? Active. So keep that in mind. You have to just keep that in mind. Your base potential cannot be more. So maybe for that reason, see, if you're a rich man, you can do 10 volt, right? But we don't want to waste money, right? 10 volt and 4 volt separately. So in future, what we are going to do in future is maybe we'll put some divider like this in future, right? So what a divider will of such type will do in future, suppose this is 6K and this is 4K and 10 volt is given, so maybe this voltage is the open circuited voltage is almost 4 volt. Are you getting? And then you can maintain BJT in what region? Active region. What happens if I make this node as a 7 volt or 6 volt or 8 volt or 9 volt like that? Then BJT will slowly enter into what region? Saturation, right? So you have to please be careful you have to look for that base potential. So see, that is the reason the BJT is drawn like this. Why the BJT is drawn like this? All of you, why the BJT is drawn in this fashion, right? The BJT is drawn in this fashion because why the BJT is drawn in this fashion? Because this should be at lowest potential. Lowest potential. Are you getting? This is 0.7 above, 0.7 above emitter. This should be at highest potential. Highest. See, that is the reason BJT is drawn like. Why BJT is drawn like this? If you draw like this, then you realize that this down one should be low, slightly above, this should be highest. Then, and please maintain enough headroom for the collector-based junction to get what bias? Reverse bias. Don't give large voltages like 6 volt, 7 volt like that. There won't be enough headroom for the collector-based junction to get what bias? Reverse bias. So this cannot be reverse here. So if this is possible, we might think it is forward, but it's not forward, mind you. You cannot have 2 volt between 5 and 10. So it makes no physical sense. Are you getting? So optimum voltage should be there at base. So slowly, with experience, you'll come to know how much voltage we have to maintain at base. Because if you slowly increase it, nicely BJT will enter into what region? Saturation. Enter into saturation. So think about it. Check the region of operation. Check the region of operation. Okay. So naturally, in the first problem, BJT was in active region. In the second problem, BJT was in saturation. So naturally, in the third problem, where will he be? The anode is at ground and the cathode is also at ground, right? So if I have anode at ground and the cathode is also at ground, now what happens? This diode is going to get off. Am I right? This diode is going to get off. Now, when is the diode on? What are the combinations for the diode to be on? So this is off. If it has to be on, then this should be positive voltage. Or even if you ground this should be at negative voltage for on. Or the anode should be at more positive than cathode, or you can give a positive here and a negative here, doesn't matter, right? It's still on. So the potential difference should always be positive. But here, what did I do? I have given base to ground and emitter to ground. So naturally, what is VE here? VE is going to be 0. See, that is the reason VD on is 0.7, VB on equal to 0.7. What do you mean by VB on equal to 0.7? Huh? What do you mean by VB on equal to 0.7? Take 0.7 only if it is on. So if it is not on, you cannot take VD on, VD equal to 0.7. Right? There has to be an anode voltage at higher potential, cathode voltage at lower potential, then only the device will get on. So this diode is off. Your VE is 0, first step. Second step, your IE is 0. Third step, your IC is 0. What is the last step, VC? The last step, VC, is 10 minus IC into 4.7. This is going to be 10 volt. Are you getting? So what is the equivalent circuit for this? What is the equivalent circuit for this diagram? The equivalent is I have a transistor and my current is 0. Am I right? Current is 0. What do you mean by current 0? The device is behaving like an off switch, right? This is collector VC. This is your VE. The transistor is behaving as an off switch. What do you mean? Why it is off? Because the current is 0. You can model this as an off switch. So the current from the supply is cut off. The current from the supply is cut off. Therefore, BJT in cutoff region. It is in what region? Cutoff, right? So now you don't have to check the other junction automatically. If the whole voltage is 10 volt here, there's 10 volt here, and there's a diode here, and naturally that junction is also off. So both the junctions are off. BJT is now in cut off. The current coming from the supply is cut off. It's in cut off region. So if you want to take V equal to minus 0.7, The other end here, this is zero, this is zero. Between 0 and 0, you cannot get a negative voltage. Are you getting? You cannot get a negative voltage. Suppose this node is at -5. What happens when this node is at -5? Then your V equal to -0.7 is valid, because between 0 and -5, you can get -0.7, right? But just because this end is ground, this end is ground, don't take -0.7 in the middle. It makes no sense. Are you getting? It makes no physical sense. Can I say that this voltage is at -0.7? Can I say this voltage -0.7 when this is ground and this is ground? No, this is wrong. Are you getting? This is wrong. Can never happen. Yeah, one more thing. For 4 volt, BJT is in active region, right? 4 volt, you increased it to 4.5, 5.5 like that. By the time you enter 6 volts, we have seen that the BJT is in what region? Saturation. I told you in analog, what do we call saturation in analog? The device is dead. The device is dead if it is in what region? Saturation. So, active means he's alive. Saturation means he's dead. Okay. But when he's still inactive, what do you mean by? Because once the gate examiner mentioned he's still inactive. What do you mean by the term still inactive? What do you mean by still inactive? Suppose if I use a statement saying that what is the age of Shockley? What is the age of Shockley when he was still alive? What do you mean by that? What is the age of Shockley when he was still alive? When I say he's still alive, that means I'm indirectly saying what is his age? What is his age? That means when did he die? Indirectly. So when the examiner says still inactive, it means that he's mentioning the edge of saturation. He's mentioning the edge of saturation, right? Find VBB such that the transistor is still inactive. Is still inactive. What do you mean by the term still inactive? EOS condition. What is EOS? Edge of saturation. The condition is called EOS. What do you mean by EOS? It's the edge of saturation. So now you understand, for 4 volt he was alive, and for 6 volt he's gone. That means in between 4 and 6 you will get the answer. That means at that point, that's a transition. If you increase slightly more than that, is saturation. If you increase less than that, he's active. So that's a thin line. There's a thin, that line is called EOS, where below which it is active, above which it is in saturation. So now I'm putting VBB here. I don't know what this voltage is, but I definitely know that it should be between 4 and 6. Between 4 and 6. So find VBB such that the transistor is still inactive. So when it's at the edge of saturation, you have to respect the active region condition here and saturation region condition. Both conditions you have to give respect, right? So tell me, what is that edge of saturation? Okay. So tell me, what is the active region condition? IC equal to beta IB, or IC by IE is beta by beta plus 1. This is the condition for active. Active. What is the condition for saturation? The condition for saturation is VC sat equal to how much? 0.2 volts. So we have to take 0.2 here, because at the edge both are satisfied. Both are satisfied. Here there is 0.7. Here there is 0.7. Now tell me, what is this voltage? This voltage is going to be VBB minus 0.7. And what is this voltage? It is VBB minus 0.7 plus 0.2. It is VBB minus 0.5. Here you have IC and here you have I. Am I right? So let's go for a substitution here. IC is 10 minus VBB minus 0.5 by 4.7K. This is IC. IE, VBB minus 0.7 by 3.3K. This is equal to 100 by 101. When you solve it, you will get VBB. You will get VBB. So what is VBB after solving this problem? It should definitely be between 4 volt and what you call 6 volt. It's around 4.76. Your VBB is around 4.76. Okay, VBB is 4.76. So what is your take on this? If VBB is less than 4.76, then BJT is in active region. If VBB is greater than 4.76, then BJT is in saturation. If VBB is exactly 4.76, then we don't know. Because exactly at 4.76, IC equal to beta IB is valid and VC equal to 0.2 is also valid. BJT is in EOS condition. What is EOS? It is at the edge of saturation. Now, in saturation, we want this diode to be on, is it not? So how is it valid that the diode is on in saturation? In saturation, mostly digital books, analog books it is 0.7 because the voltage does not change. In digital books, this is 0.8. This is given as how much? 0.8. And here there is 0.2. And here you have a diode. So if this is ground, this will be 0.2. This will be 0.8. Then here the drop is around 0.6. So this also is on. That is what they say, right? But in my opinion, if you take, even if it is 0.5 here, right? Even if it is 0.5, it doesn't matter, right? Don't worry, because our assumption here was 0.7. But VB cut-in is 0.6, VB active 0.7, VB saturation 0.8 in digital books, right? But for calculating currents and voltages in gate problems, he generally takes how much? 0.7. So don't worry, right? Don't check the diode. That is not the correct way of checking saturation. This diode is on, that diode no. You have to prove that the base current is more, or beta forced is what you call less than beta active. So that is the correct. Are you getting? So don't worry about this, right? Okay, so do you remember the procedure that I told you? What is the procedure? What are the steps? What are the steps? Tell me how you will calculate VE, IE, IC, VC. Are you getting? VE, IE, IC, VC. Tell me VE, IE, IC, VC. Am I right? So with that, VE, IE, IC, VC, can you orally do this as an exercise I'm telling you? Let me make this simple by saying that beta is large. What do you mean by beta large? Your IE is same as IC. Your IE is same as IC, and your IB is neglected. Your IB is what? Neglected. So just tell me orally, right? Don't worry. Slowly you can tell. Slowly you can tell. Orally you have to tell. If I give some voltage, do you know how to calculate voltages now? Suppose I give say some voltage, right? Like 4 volt, right? Say this is 12 volt. So how much will be this voltage here? 3.3, like that. Are you getting? So what if I give 3 volt, right? Then how much is this voltage? 2.3. So like that you can calculate, right? And once you get VC, base current is 0. It's neglected. So that the VC here, you can give it to the other BJT here. You tell me, I will write some resistor values. Can I make 2.3K? And you know why I did it, why did I put, right? Our analysis will be simple. Then I'll put 4K here. 4K. Then 3.65K. 3.65K. 5K. 5K. Not 5K. 1K will put. 1K. 2K. 5K. Something like this. Okay. Now, as I go up, the voltages should be in increasing order. So let's see if you can do it orally, right? This is Q1, Q2, Q3, Q4, Q5. So we'll do it slowly, right? So if this is 3, what is this first step? VE. What is VE1? Tell me. What should I write here? What should I write VE1? How much? 3 minus 0.7, 2.3. 2.3. Then what is this current? 2.3 by 2.3K, 1 milliampere. If this is 1 milli, this is also 1 milli. Am I right? So what is 12 minus 4? 12 minus 4 is going to be 8 volt. Am I right? So any problem? 3, 2.3, 1 milli, 1 milli, 8. 8 minus 0.7. What is 8 minus 0.7? 7.3 volt. Then what is this current here? What is this current? It is 7.3 by 3.65. Is my mathematics correct? What is 7.3 by 3.65? So, what is 7.3 by 3. No, is my oral mathematics is correct? Because I wanted instead of 1 milliampere, 2 milliampere. So this is approximately 2. If this is 2, this current is also 2. 12 minus 2. What is 12 minus 2? This is going to be 10 volt. Am I right? 10 volt. Then what is 10 minus 0.7? 10 minus 0.7, 9.3 volt. Oh, I missed the mathematics. You have to help me now. What is 9.3 by 7.3? 9.3 by 7.3. Somebody with a calculator help me. What is 9.3 by 7.3? 9.3 by 7.3. 1.27. Thank you. 1.27 milli. Thank you very much. So this is also 1.27 milli. So how much is this? What is 12 minus 1.27 into 2K? 12 minus 1.27 into 2K. 12 minus 1.27 into 2K. 12 minus 1.27 into 2K. So that is 9 point. How much did you get? 9.46. Okay. This is around 9.46. Then remember there are two diodes here. Two diodes. 9.46. 9.46 minus 1.4. Two diodes are there. What is 9.46 minus 1.4? 9.46 minus 1.4. That is 8 point or 7 point. How much? 7.0. 9.46 minus 1.4. 7.06. Am I right? Is it okay? What is 9 minus 1? 9 minus 1 is 7 or 8? It is 8, no? 8.06. Okay, very good. So let's repeat this. I'll change the color of my pen. Very good. So it seems we are together, right? So how did we solve this orally, right? We didn't do any complicated thing, but can you imagine 1, 2, 3, 4, 5 diode problem? Can you imagine a 5 diode problem? It would be very complicated, right? But look at BJT here. BJT, so many stages. We just took a pen here and we said, this is my first step. Okay. So what is my first step? 3 minus 0.7, 2.3. And what is my second step? My second step says that 2.3 by 2.3K is 1 milli. And my third step says that 1 milli, and this is also 1 milli. And my fourth step says that 12 minus 4 is going to be 8. So any problem with the first stage, right? No. The second stage says that, this is fourth step. The fifth step says that 8 minus 0.7 is 7.3. The sixth step says that 7.3 by 3.65, that is going to be 2 milliampere. And my seventh step is the same current. And the eighth step is 10 volt. The eighth step says it's 10 volt. The ninth step, ninth, how do you write 9 in Roman? 1x, right? Yeah, the ninth step says that it's 9.3. The 10th step is 9.3 by 7.3, that's 1.27. 10th, and my 11th step is 1.27, and my 12th is 9.46, and my 13th step is 9.46 minus 1.4, that is 8.6. So which is better? Ohm's law is better or KVL? If you can do by KVL also, it becomes a lot cumbersome when you're applying the loops. Are you getting? So any doubt, any doubt, any doubt, any doubt? Any doubt, right? Now, all of you, we have to see whether BJT is in active or not. If it's not in active, we have to make some changes in the diagram, right? The first step, Q1, let's see. As I go up, the voltages should be in increasing order, right? So 2.38, 8 is greater than 2.3. This is in active. Active. Am I right? The second one, 10, 7.3. 10 is greater than 7.3. This is also in active. Right? See here. Q3 transistor, at least 0.2 volts should be there. We had 9.3, but we got 9.46 there. So what change can we make in the diagram, right? So any change that you want to make in the diagram here, shall we change this resistor 7 point, let it be here. Instead of 2K, please let us make it 1K. Instead of 2K, just make it 1K. 1K. Then what will happen? 12 instead of 9.46, this is going to be 10.46. This is going to be 10.46, and 10.46 minus 0.7, that is 1.4, 10.46 minus 1.4. So how much is 10.4? It's going to be 9.06. Okay. So now the third BJT is also in what region? Active. What about the fourth one and fifth one? There's no need to check because collector is given to 12 volt directly. Emitter is less. So this is also in what region? Active. So now you can take down this question. Are you getting right? So please repeat this again as a homework, right? 3 minus 0.7. Please say it in your mind again and again. VE, IE, IC, VC. VE, IE, IC, VC. VE, IE, IC, VC, right? 2.3, 1 milli, 1 milli, 10, 12 minus 4, it is 8. Then you go to the next stage, 8 minus 0.7, 7.3, 2 milli, 2 milli, 12 minus 2 is going to be 10. 10 minus 0.7, 9.3, 1.27, like that. Are you getting? And then finally, 10.46 minus 1.4, two diodes are there. It is going to be 9.06 volt. So all the BJTs are in what region? Active region, right? Now please, base current is neglected. There is no IB there, even if there is any resistor or whatever it is, right? So the IB is neglected. Remember, the IB is neglected. The base current is neglected. Now what is 12 minus 1.27? All of you? What is 12 minus 1.27? 12 minus 1.27, because that's 1 milliampere there. 12 minus 1.27. This voltage. What is this voltage here? It is going to be 12 minus 1.27. That is 10.73. 10.73 minus 1.4. 10.73 minus 1.4. What is 10.73 minus 1.4? 10.73 minus 1.4. 10.73 minus 1.4. $10.73 minus 1.4. 9.33. Have you got, everybody? 9.33, right? Yeah. Please check. It's just a matter of numbers, right? And please don't forget VE, IE, IC, VC. As you go up, the voltages should be in what order? Increasing order, right? Now, let us do the same with the PNP transistor. With the PNP. So please don't forget, all of you, what is the procedure? NPN or PNP, doesn't matter. Tell me, what is the procedure? VE, IE, IC, and VC, right? If you want, you can take a negative voltage also here. So because this is our first problem in PNP, we are going to do this step by step. We are going to do this step by step, right? Step 1. Step 1. So this is your PNP transistor, and the diode takes a drop of how much? 0.7, right? So PNP transistor given beta equal to 100, VE beyond 0.7, check the region of operation. Check the region of operation, right? Tell me, what is step 1? This node from here, VE minus 0. What is VE minus 0? 0.7. So your VE equal to 0.7 volts. This is the first step. Step 2. IE. What is IE? It is 10 minus VE by 5K. What is IE? It is 10 minus VE by 5K. 10 minus VE by 5K. How much do we get? This is around 1.86 milliampere. Step 3. IC. It is beta by beta plus 1 times of I. It is 100 by 101 times 1.86 milli. This is around 1.84 milliampere. Step 4. Last step, VC. What is VC here? What is IC here? IC is nothing but VC minus of minus 10 by 1K. What is VC? Right? Just tell me logic. If you go up, your voltage will increase. Am I right? If you go up, your voltages are going to increase. So VC is minus 10 plus IC into 1K. It is going to be minus 10 plus IC into 1K. So 1.84 minus 8.16 volts. Minus 8.16 volts. So now tell me, did we change the analysis here? Nothing. You should look for emitter to base junction. You should look for what junction? Emitter to base, right? So this is already given 0.7. So once this is known 0.7, V is 0.7, IE is 10 minus 0.7 by 5K, IC is almost equal to IE, 100 by 101, and VC is minus 10 plus that drop. So it's time to check whether we have done it correct or not. Now tell me, what are the numbers between minus 10 and plus 10? Minus 10 and plus 10. You can have minus 9, minus 8, minus 7, you can have 0, 0.7, and then 1, 2, 3, 4, up to 10, right? This minus 10, this node is at minus 8. This node is almost 0, 0.7. Is it correct? Does it make any sense? Yes, true. Minus 10, minus 8, minus 7, minus 5, 0, 1, 2, 3, 4, up to 10. So what is VEC here? What is VEC? VEC equal to VE minus VC. It is 0.7 minus of minus 8.16. It is 8.86 volts. So don't underestimate 0.7. Don't underestimate 0.7. 0.7 is at least 8.86 volts at a higher potential than minus 8.16. So is VE greater than VC? True. Therefore, BJT is in active region. BJT is in active region because your emitter is at a higher potential than collector. Now, I told you the base potential is one such dangerous thing. What about collector loads? Here you can see that the collector load is at 1K. What if I interchange the resistors? What if I interchange the resistors? Do you think the BJT will still be in active region? Follow the same procedure. VE, IE, IC, VC. Follow the same procedure. VE, IE, IC, VC. Check the region. Okay, so let's carry on the same procedure. V 0.7, IE, huge current 10 minus 0.7 by 1K, 9.3 milli. Third step, IC, beta by beta plus 1 times 9.3 milli. This is around 9.2 milli. And fourth step is VC equal to minus 10 plus IC into 5K. Oh my God, this is positive. There's around 9.2 into 5 minus 10. This is around 9 5s are 40, around 36 volt. This is around 36 volt. Just tell me, does it make any sense? Does it make any sense that you have a transistor? This end is connected to ground. This end is this, minus 10 and plus 10. Here you have 0.7. 0.7, you can approximate it to be 0. So between 10 and 0, what is this voltage? Between 10 and 0, this voltage should be anywhere between 10 and 0, but we got 36 volts. 36 volts. So does it make any sense? Does it make any sense? Huh? In the comment section, somebody has written nonsense, right? It is true. Between 10 and 0, it is nonsense. But don't write nonsense. It makes no physical sense. It makes no physical sense. Even if you conduct this experiment anywhere in the world, right? You can go to Russia, you can go to Sahara Desert in Iceland, wherever. You will never get minus 10 and 0.7. You will never get 36 volt, right? So there's only 20 volt headroom here between minus 10 and plus 10. So you cannot get a 36 volt drop, right? Makes no sense. So that means your assumption that BJT is an active region is false, right? So BJT is not in active region. BJT is not in active region. It makes no physical sense. It makes no physical sense. BJT is not in active region, right? Good. So now we have to check for saturation. We have to check for saturation. In saturation, we know that this voltage is 0.7 and the voltage here is going to be 0.2. The voltage here is going to be 0.2. And what are the numbers here? This is 1K. This is 5K. This 5K. So tell me what is VE? VE equal to, it is 0.7 volt. V equal to 0.7. If you come down, you have to subtract. It is 0.7 minus 0.2 is going to be 0.5 volt. So what is IE and IC individually? What is IE and IC individually? IE equal to 10 minus 0.7 by 1K. This is around 9.3 milliampere. What is IC? IC is 0.5 minus of minus 10 by 5K. It is 2.1 milliampere. Now all of you have that soldier analogy, the soldier analogy I told you, 9.3 milli. 9.3 milli means 93 soldiers have started their journey. 93 soldiers have started their journey. And how many have reached the collector? 2.1. Only 21 soldiers have come. Look at the huge base current. The base current is more than the collector current. So how many are dead in the base region? IB equal to IE minus IC, which is 9.3 minus 2.1. It is 7.2 milli. So what is beta forced? Beta forced is IC by IB. It's going to be 2.1 by 7.2. So what is 2.1 by 7.2? So that's not even 1, right? So it's not even 1. Any calculator? 0.291. Oh my God. Can you ever imagine a BJT with this beta, 0.29? So that's beta forced is much less than beta active. Beta active is 100, beta forced is 0.29. So BJT is in what region? Saturation. BJT is in saturation. So see how I can directly tell that this is wrong. How I can directly tell this is wrong. The moment you see a problem, when this node is at 0.7, see this node is at 0.7, there is 9.3 milli flowing, right? If your IE is approximately IC, 9 5s are 45. The same 9.3 will flow here. If this is 9.3 here, then 9 5s are 45. How will you get a 45 volt drop between minus 10 and plus 10? By inspection, we can, without calculating anything, we can say this, the IE is around 9, right? May not be 9.9, approximately 9.3. 9 5s are 45. 45 volt drop. So it makes no sense. You have to just stop the assumption that these two currents are same. Because these two currents, if they are same, then your IC is beta IB. IC is beta IB. Your IC by IE is beta by beta plus 1, right? So that is true only in active region. But here, this is definitely in saturation. And please remember, these are the correct numbers. These are the correct numbers. If the examiner asks you what is the base current, you have to do this, right? BJT is definitely in saturation. It is in saturation. So please repeat all the problems once again at home. VE, IE, IC, VC. VE, IE, IC, VC. Are you getting? VE, IE, IC, VC. VE, IE, IC, VC. Right? So as a homework I'm giving, but you can do it orally. You can just do it orally here. It's just as a homework, right? You can do it orally. Just tell me what is the answer orally. Orally tell me. How much is this? How much is this? Louder, louder, right? 3.7 minus 0.7. How much is this? 3. 3 by 1.5, 2 milli. This is 2, this is also 2. So 6, 10 minus 6 is going to be how much? 4. And 4, that's it, that's the answer. Because 2 diodes are here. So if you have 4, how much is V0? So that's a homework. This is 4. What is V0? 2 diodes, right? Okay. Okay. So just for fun I've given. I know you can do it orally, right? So 3.7 minus 0.7 is 3. 3 by 1.5, 2 milli. This 2 milli. 3 2s are 6. 10 minus 6 is 4. 4 minus 1.4. That is okay. That's the answer. Fine. Okay. So shall we stop for today? It's around 9 o'clock. So you can have some questions if you wish. Okay. So if you have doubts, you can ask me. Venkat, unmute. Chandy, please unmute the students.
Okay, sir. Okay.
Yeah. Thank you, Venkat.
Good evening, sir.
Yeah, good evening.
Sir, in page number 26.
Page number 26.
Yes, sir.
Okay. Yeah.
Sir, my connection got disturbed. Can you please explain this question again?
Yeah, I said in which region the BJT is working here. The base is grounded. Can you see?
Yes, sir.
Emitter is grounded. Ground means, remember, it is 0 volt. Okay. Ground means how much? 0. So base is 0, emitter is 0. So
Yes.
between 0 and 0, emitter should also be 0.
Yeah.
You cannot get minus 0.7 there. But if base is at positive voltage, then emitter will be some voltage. Or if emitter is at negative voltage, the diode is on. For the diode to be on, base should be positive or emitter should be negative. So we can make a note here. We can make a note here. Note for base emitter junction to be forward. To be forward, your base should be positive, or either emitter should be what? Negative. Are you getting?
Yes, sir.
Yeah.
Okay. And sir, is there any method which we can use by directly looking into a circuit that it is supposed to be in saturation or in active, and we have to solve using that?
In saturation,
Yes, sir.
your IB current, your base current is increasing, right? So that means by looking at the circuit, you can, if your collector resistor is of a very large value, suppose simple, this 4.3 is there, no?
Yes,
Instead of
sir.
4.3, somebody puts 1 mega ohm. Then, if your emitter is 1 milliampere current, if the same 1 milliampere current flows in 1 mega ohm instead of 4.7, there is a 1000-volt drop there. So, can you get 1000 volts drop? It's very
No.
difficult, no? With 10-volt supply, can you get 1000 volts drop? It makes no
Yes.
physical sense. So, you have to see if your collector resistor is getting larger, then there is a danger. Then there is a danger. Okay. So, because you mentioned it, I will summarize that also. So, saturation, right? This is your doubt. For saturation, beta should be low. Beta is IC by IB. Am I right? So beta will decrease for saturation. So if beta has to decrease for saturation, your IC can decrease or your IB can increase. IB can increase or IC can decrease. Now, how IB will increase? We have seen that the base voltage increases, your base current will also increase. Naturally, Ohm's law. VB increases, IC increases. Increases. IC will decrease. IC has to decrease. Are you getting? When IC, if IC decreases, that means your RC should increase. If RC, if you put a large collector resistor, then also the BJT will go to what region? Saturation.
Saturation region.
So finally, conclusion is, if you have larger base voltages or if you have larger collector resistors, then you can doubt that circuit that is going to saturation.
And so in yesterday's lecture, I didn't understand the trigger circuit of.
Trigger is, trigger is just to change the state. A trigger is just to state, it's the op amp who's going to change the state. The trigger is only to give a voltage of less than 0.7. Less than 0.7. So what was the trigger basically? It is just a switch connected to ground, no? Yes or no?
Yes,
So when you close it, that point will come down to 0. That's it. And the other end there is 0.7, 0. So naturally the state will change. Simple.
Okay. And also, sir, I didn't get these multi-vibrators, how they start from the first phase? If there's no source, so how do they start when?
Noise. I've told you in positive feedback, even if you don't give any input, when you switch on, even if the output is like 1 millivolt, then if V0 increases, your V plus will increase. Again, V0 will increase. Your V plus will increase. Again, V0 will increase.
Okay, so it sets on saturation.
Yeah, it will go to saturation.
Okay.
Even without input.
Okay.
Okay.
Yes, sir. Thank you so much, sir.
Hello. Sir, I want to know the early effect. I'm confused. What is early effect?
See, if you have an NPN transistor, emitter base collector, between N and P there is a barrier. A diode will tell you that if you have an N material, there is a P material, there will be a depletion. It is called what? Depletion. So similarly, collector base junction also there is a depletion region. The width of depletion region will increase if you give more reverse bias. For example, I have a diode like this. I have a diode For this diode, somebody has given 1 volt. For the same diode, somebody has given 10 volt. In which diode there will be more depletion width in reverse bias?
10 volt.
10 volts. So naturally, in a transistor also, when the collector base junction is reverse bias, the depletion width will change for different load values. Suppose if I keep on changing the load, this RC, naturally what will change? VC will change, no?
Yes, sir.
This is 0.7 only. And this voltage is going to be VC minus 0.7. It is going to be because the whole voltage is VC. This VCB is VCB. VCB is VC minus 0.7. So for different RC values, your VCB is different. Your VCB is different. So for some circuit, your VCB is this much width, 4 volt. For some other, it can be up to 9 volt also, right? As the potential increases, the width will increase. When width increases, previously, suppose this is your base width for recombination. Now the base width, as the depletion width keeps on increasing, the effective base width will reduce, no?
Yes, sir.
So when the soldiers go from here, when the electrons travel to the P region, during recombination, only few will die. Only few will die here, but here more will die. So that means here IB is less. Who is here? The loss is IB only, no?
Yes, sir.
Our main aim is IE should be IC. Yes or no?
Yes, sir. Yes, sir.
IE should be IC. So in between the travel, IB is going to lose. You're going to lose more IB if there is more base width.
Okay.
So that is why when you draw the characteristic, for different voltages, the currents are different.
Okay.
IC is different.
So basically, it's when we
Base width modulation.
sir, when we increase the VC,
Yeah.
yeah.
See,
Then-
as VC keeps on changing,
Yes, sir.
the VCB will keep on changing.
Yes,
Here,
sir.
the effective base width will keep on reducing.
Yes,
So
sir.
when the electrons come here, travel like this, the different IE flowing. It's a surprise that IE will think, "Arey, different IE is coming to, different ICs are coming from the emitter, from the collector region. From emitter, they have to go to collector, no?
Yes, sir.
The word collector says that they have to collect the charges there. So the emitter from the different collector currents you are getting for different voltages because the IB is changing.
Yes.
But don't worry, in analog we are going to remove this. I'm going to pull this line parallel to x-axis.
Okay. So, sir, basically, it's when we increase VC, the band of the base will decrease, and due to which
Yes,
IC
yes.
will increase.
That's all.
Okay.
The recombination will change.
Yes,
The width is decreasing. That is called the base width modulation.
Yes.
You're right.
Okay, sir. Thank you, sir.
Yeah.
Hello, sir, in 28F.
Hello. Hello.
28F, sir.
Yeah.
Sir, here I get a small doubt that can't we find VPB by only VE minus VC?
VEE. Where is VEE?
VBB, sir. VBB.
VBB is there.
Ha.
IE and IC are almost same. So this is VBB minus 0.7, VBB minus 0.7.
Yes, sir, that is what I'm getting. But can't we find, like, I get the equation as VBB minus 0.5. Minus of VBB minus 0.7 is equals to 0.2.
VBB minus 0.7.
0.5 minus VBB minus 0.7. That is the potential at positive and the potential at negative. I subtract them and equate by 0.2.
That's what I'm saying. This voltage minus 0.2 is going to be VBB minus 0.7. You're right.
No, sir. This voltage is VBB minus 0.5 minus of VBB minus 0.7 is equals to 0.2.
Of course. This voltage minus this voltage is 0.2. Yeah, you're right.
Yes, sir. But I'm getting the different answer. I'm getting VBB is equals to 1 volt only. By this.
VBB, you're getting 1 volt. What is the final equation that you have used? Did you use IC by IE equal to beta by beta plus 1?
No, sir. I used VE minus VC is equals to VCE.
VE minus VC. Yeah, with that you will get only with that what will you get?
VBB. Sir, the potential at the upper point is VBB minus
The
0.5.
VBB is getting cancelled, no? VBB minus 0.5 minus of VBB minus 0.7. Your VBB,
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes,
yeah,
sir.
yeah,
I
yeah.
get,
Your VBB
I
is
get
getting
that.
cancelled. You have only 0.2 there.
Yes, sir. Yes, sir.
Yeah, yeah, yeah. Okay.
Hello, sir. In multi-transistor problem, NPN.
Sir. 1 second, sir.
Hello.
One more request.
Uh,
So actually, I just want to request Venkat sir that kindly unmute us one by one. Exactly, it is creating a hodgepodge when we are when you completed one doubt. Then all of us will create a shout that sir.
But is it not in my hands to do it?
Sir, you can also do
Yes, sir.
it.
You can do that.
Oh, okay.
Previously, only Narsamma sir is doing that.
Oh.
Yes, sir. You can also do.
I can also do it, right?
Okay, sir. Okay, thank you, sir.
Yeah. Thank you.
Sir, in that multi-transistor problem, if the Q2 and Q3, if the center BJT is in saturation region, the further
Then the
Q3
base
and
current will
Q4.
increase, no? We have to again calculate. For such a big problem, it will create a problem now for me.
Okay.
Yes or no? Because I have not started PNP yet. So why to get stuck in that big problem? One transistor is active, one transistor. So I try to maintain all the transistors in active region such that my IB is neglected. The main fundamental idea is what? IB should be neglected. But in saturation, is your IB neglected? No. Your IB is greater than IC by beta. Yes or no? Then that
Q3 and Q5 will be not off, no? Yeah.
Here Q5 will not be off because 10.73 you are giving here, no?
Yes.
10.73 minus 1.4. What is 10.73 minus 0.7? This voltage is going to be 10.03. 10.03 minus 0.7 is going to be no. How much is this? This is not 10 point. How much is this value?
10.73.
10.73 minus 0.7 is 10.03. No.
Yes, sir.
10.03 minus 0.7 is going to be 9.33. Are you getting?
Yes, sir. Yes.
Yeah.
Okay, sir.
Sir,
And we have 12. So it is inactive. Yeah. Tell me.
hello, sir. In page number 33.
Yeah.
Sir, you said that if the examiner gives in PNP, we can convert into NPN, no, sir?
Yes. Tomorrow I will tell. No. We will take even differential amplifiers tomorrow, and we are going to convert NPN to PNP and do it. Here also you can do at home.
Is it by simply changing the...
First, you should know how to draw this transistor like that. That's enough. Are you getting? After drawing here, where is emitter given? Where is emitter
plus
given?
10.
1K.
Plus 10.
1K. So 1K you connect here. This end is minus 10 volts. Here what we have to connect 5K, and this is plus 10. This is ground. Same answer you will get. Tomorrow we will do. Okay.
Yes, sir. Sir, in page number, I don't know the number, sir, but can you explain how in PNP the diode between the collector and base is reverse bias, sir?
Yeah. See, this is a PNP transistor.
Yes, sir.
And this is a PNP, no? Yeah.
Yes, sir.
Yeah. This is PNP. All right. So where is V? V is 0.7. This is 0.7. This is ground, 0. This is a diode direction. And here P material, what is VC?
Minus.
What is VC? Yeah. No, this is in saturation, no?
Yes, sir. Minus 8.4.
So where is active problem? Yeah, this is active, no?
Yes, sir.
Yeah. This is a diode. Here the voltage is 0.7. This is a PNP. So this is P material. Now you tell me. P material is at minus 8.
Yes, sir.
Cathode is at ground. So that means this is what bias? Reverse only.
Reverse bias.
Yeah, that's all. This is inactive.
I understood in this, sir. You said previously the voltage will be increasing from the downward.
This is minus 10. This is plus 10. As you go up, the voltages are in what order? Increasing, no?
Even in the
minus
NPN also, no, sir?
Whether it is NPN, no, even for resistors, forget about NPN and PNP. If you have two resistors like this, the same thing it is going to behave. Suppose I am having two resistors like this, three resistors. I
Yes,
told
sir.
you, know, if I give VCC here, what will be the voltage if it is R? This is going to be VCC by 3. This is going to be 2 by 3 VCC.
Yes, sir.
0.66 VCC. This is 0.33 VCC. As you go up, any circuit will have increasing voltages.
Yes, sir. Sir, here you said from the diagram beside it is on the left side. IC is entering and IE is leaving, no, sir.
Yeah.
But in the square, the box you have drawn here IE is entering and IC is leaving, no, sir.
Where? This is electron current, no? Conventional current is in the
Okay,
opposite.
yes, sir. Yes, sir. Yes, sir.
Yeah. Good.
Thank you, sir.
Hello, sir.
Yes.
Sir, I have a doubt on a day before yesterday class.
Okay, tell me if I remember.
Sir, actually, motor, you explained motor now, sir.
Yeah.
Sir, we will give motor to V in or V2, sir.
We will give motor to
V input V or inverting V terminal, sir.
no, we don't give it to input. That is a tank water level.
Okay.
The plus VSAT and minus VSAT is going to drive the BJT, no?
Yes, sir.
Yeah, from there the motor is going to get on.
No, sir. Actually, if you give to inverting terminal, if it exceeds the,
It is only to check the resistance. This is the circuit you are saying, no? This one, huh?
yes, sir.
Here there is a relay, 230 volts. Here we will connect motor. The relay, there is an inductor, no? Have you seen a DC relay?
No, sir.
You have to, if you buy a DC relay, then the relay coil will be there. This coil, once it gets energized, the normally open contact, NONC will be there. Normally closed, normally open. Through normally open contacts, you connect 230 volts. Then other end, you give it to a motor here, like this. So once the op-amp output goes to plus VSAT here, plus VSAT, what will happen? You can put a current limiting resistor, IV will flow. Then your IC will flow. Once IC flows, the relay gets energized. The contacts will be closed. Circuit will close. Motor is on.
Actually, in that on that day you gave the motor to inverting terminal and.
No. I gave a tank here.
Oh, okay, sir. Okay, sir.
This is a water tank. This is a reference. Motor is here.
That I got confused, sir. Why you give?
This is a water level. Some conductor will put as it keeps on increasing. Or you can do one thing. Can you down part you put one conductor, upper part let it be open. Once it touches, circuit will close. No, like that also you can do.
If in non-inverting Schmitt trigger, where we will give that motor, sir, the tank, sir.
Non-inverting you want to give her.
Yes, sir.
So why you want to give? See, it should have only two thresholds, no? UTP and LTP. The
Yes,
input is nothing but the input is nothing but the water level.
Yes, sir.
This is the water level. Why you want to connect there? The hysteresis is in anti-clockwise, no?
Okay, sir. Okay.
Negative you will get. There again some reference voltage we have to connect unnecessarily.
Okay, sir.
Hello, sir. Good evening, sir. Sir, op-amp draws no current due to high input impedance, na, sir.
Yes.
But in CCCS and CCVS, we have low input resistance. So,
see, op-amp, this is op-amp. Okay.
yes, sir.
Op-amp is VCVS. It is what?
We see voltage control voltage source.
From here, we will create 4 types. VCVS, CCCS,
CCVS.
CCS and CCVS.
Yes, sir.
This is VCVS for open loop. Open loop. That means when you buy op-amp, it is VCVS only.
Yes, sir.
But this is with feedback, with feedback, with feedback, with feedback. Once you connect feedback, op-amp will give 4 types. So how it is going to decide? If you give series shunt feedback, series shunt or voltage series feedback, this is shunt series. This is series.
Yes.
This is shunt. Are you getting?
Yes, sir.
So how to recognize feedback? We will see in feedback amplifiers.
Okay, so inbuilt it is an open loop.
Open loop, what you said is correct. Input resistance is very high.
High.
Output resistance is 0. It is VCVS only.
Yes, sir.
So when shopkeeper is giving you op-amp, he is giving you VCVS. But after coming home, you connect feedback. You can have 4 types.
Yes, sir. So in that feedback, it draws current, right, sir?
What? Yeah, it will draw current and send it to the feedback path for processing, analog processing.
Sir, another doubt, sir. 8F, sir. 8F.
Yes.
Yes, sir. Sir, sometimes you're writing suffix C is small and sometimes C is capital, sir. Here slope, you're written in denominator capital VCE, sir.
Where? This one, huh?
Yes, sir. Right.
See, if I write only VCE capital, it is DC.
Yes, sir.
If I write V small c small e, it is instantaneous value.
AC.
Yeah, you're right.
Okay, sir. Sir, your teaching is very nice, sir.
Thank you very much.
Make the thing simple, sir. Sir.
Thank you so much.
Thank you, sir.
Yeah.
Hello, sir.
Yes. What's your
Sir,
name?
I am Gopal, sir. Gopal Sekar.
Okay.
Sir, I had a doubt in 25F, sir, page number.
Yeah.
Yes, sir. Sir, here where you gave the base voltage through the VCC, sir, did you apply voltage divider rule here, sir?
Yeah. Roughly, I am telling. If I neglect the base current,
yes, sir. That's
my
what.
beta is large.
Okay.
If my beta is large, then roughly my voltage is going to be 4 volt.
Okay, sir. Okay. That's it. Thank you, sir.
Okay.
Thank you very much.
Yes.
Hello, sir.
Yeah.
Today's first problem.
First problem.
Yes, sir.
Yeah, tell me.
This is not understood, sir.
What you have not understood? These characteristics are?
Vout equal to how 3.3.
Is a substitution you have to do. First you substitute. See, can you see the range here?
I see.
So you substitute V in 2. 2 minus 2, 0. 0 square is 0. V naught is going to be 10. So when V in is 2, your V naught is 10. Can you see when V in is 2, V naught is 10?
Yes, sir.
Similarly, when V in is 3.3, your V naught is 1.3, somewhere. Okay. This is the characteristic.
Okay.
Okay, we don't want that characteristic. What we want is a solution. In the solution, the examiner is asking, find V in if V naught DC is 5. Okay. So 5 volts we have substituted here. V naught is 5. 10 minus 5 into V in minus 2 whole square. V naught is 5. Then your V in is going to be 3. If you want to substitute V in 3 and
Okay.
3 minus 2. What is 3 minus 2? 1. 1 square 1. 5. 5 into 1, 5. Are you getting? Yes or no?
Okay,
Right.
sir.
So your V naught is going to be this value. Yeah. So when V in is 3 volt, your V naught is 5 volt. This is the operating point. At that point, he wants voltage gain. And how do you define voltage gain? Voltage gain is not V naught by V in. It is delta V naught by delta V in. What is delta? It is differentiation. dV naught by dV. So I think you know how to differentiate this value, no? Yes or no? So what is dV naught by
Yes, sir.
dV? Differentiation of constant is 0. It is going to be 5 2s are 10.
0.
10 into V in minus 2. That's all.
Okay, sir. Understood.
Yeah.
Hello, sir. Hello, sir.
Yes.
27, sir, page. 27.
Yeah.
Doubt.
Sir, in that, check the region of operation.
Yeah.
How cut off, sir?
No current is flowing, no? Diode is off. This diode is off because base is grounded, emitter is grounded. No input is given, either to emitter or to base. Then how BJT will work? This emitter voltage is 0,
Okay, sir.
IE is 0, IC is 0, everything is 0. So when no current flows, 10 volts will appear here, BJT is in cutoff.
Okay.
0.
Sir, in that next problem, 28.
Yeah.
When we find you are taking IC by IE, sir, edge of saturation.
No, IC, this has come from IC equal to beta IB. So IC equal to beta IB means IC by IE is beta by beta plus 1. Are you getting?
Yes, sir.
Yeah. So you have to respect active region condition as well as saturation region. Active region IC is beta IB. Saturation region condition is what? Your VC is 0.2. Are you getting?
Yes, sir. Edge of saturation means IC equal to beta IB.
At the edge of saturation, IC should be beta IB, VC also should be 0.2. Because at that edge, you don't know whether it is in saturation or inactive.
Okay.
Are you getting? Edge means what?
Okay.
Left side saturation, right side active. You are at that thin line. Are you
Okay,
getting?
sir.
Yeah.
Hello, sir.
Yeah.
Sir, can you please just go to 25 page, sir?
Yeah.
Sir, here, can you explain the statement that one, sir? Look carefully the base potential to stay inactive.
Yeah. In future, I want you to see the base potential I'm saying. Like base potential should always be less. Don't think you should give large base voltage. If you give large base voltage, BJT will go to saturation. That's what I mean to say.
Okay, okay, sir. Sir, in the
Okay.
last problem, sir, in 34F,
Yeah.
34. Oh, yes, sir. Sir, here in the second part, sir, checking for saturation. Here the base is grounded, na, sir.
Yes, yes.
Instead of grounded, if it is 6 volts, then VE
If
must
this
be
is
6.9, na, sir.
Yeah, if this is 6, emitter will be 6.7.
Then
Collector will be 6.5.
6 plus. No,
If
sir,
base
I am
is
saying
cold,
emitter will be.
emitter will be
Sir,
6.7.
your what?
Huh?
6.7 plus 0.2 volts is also added, na, sir. Yeah.
Yeah, then 10 minus 6.7 by 1K, around 3 milliampere will flow. IE. Accordingly, you can check what is that. Okay. Yes.
Hello. 30F.
Yeah.
Sir, why you have changed the resistor, sir, in third case? I mean,
See, for
the
active
transistor
region,
3.
your collector should be at higher potential than emitter. Yes or no?
Yes.
So when
Yes,
I
sir.
came to the
Then
third Q3, collector is not at higher potential than emitter. That means BJT will go to what region?
then it's 9.46. Yes, sir. 9.46 is greater than 9.3 only, no, sir.
But it is not 0.2, no, it is less than 0.2.
Yes,
The
sir.
voltage
So,
is
okay.
0.2, that means it is in saturation, no?
Yes, sir.
Yeah, anything
Sir,
above
in every
0.2 is
case, we
okay.
have to take.
What?
Sir, in every case, we have to take 0.2
See, the examiner is
saturation,
saying,
sir.
why it is not my value. Examiner says if it comes down to 0.2, finish. The device is dead, it is in saturation. In some gate problems, he says VC sat equal to 0.1. In 1 or 2 gate problems, he says VC sat equal to 0. So if you touch that voltage, that means the device is in saturation. Okay, examiner will give you.
Sir, today's homework. Okay, sir.
Homework means
Today's homework. Yes, sir, but
yeah, tell me. This is 3.7. That means this should be 3. Yes or no?
that, sir, here you are. Okay, sir, that one. Here you are saying directly after that minus 1.4, no, sir. How you are saying directly minus 1.4?
Minus will not come. This is ground. This is 10.
In the last case.
It will not come. Minus and all will not come. See, this is 3. This is 2 milliampere, no? This current should also be 2. 3
2
2s are
milliamperes.
10
There will
minus
be 4. Yeah.
Very good. 4. 4 minus 0.7. 3.3, no?
3.3.
3.3 minus 0.7. 3.3 minus 0.7 means 4 minus 1.6. 2.4. 4 minus 1.4. 2.6.
Okay, sir.
Are you getting?
Yes, sir. Yes, sir.
That's all. That is the answer.
Sir, in active, if we got active region, there will be 0.2 volts, sir. I mean, we had to consider that also.
For saturation.
If
If it is not inactive, for checking saturation, we have to put 0.2.
Okay. If it is active, we should not take that.
No, if it is active, there will be a big large voltage. No, see, for example, 4 volt, 3 volt. Can you see 4, 3? How much voltage is there? 0.2 or 1 volt?
1 volt.
So circuit will give no 1 volt. Some circuit
Okay.
4 volt, 5 volt, 6 volt.
Okay.
Yeah.
Thank you.
Hello, sir.
Yes.
Sir, a minor doubt, sir, means like if nothing is mentioned, then we will take V saturation as VC saturation as 0.2 volt and solve.
So he has to give. Generally, you can take 0. Nothing is mentioned.
Okay, means like by default, what we will take if nothing is given.
Most of the gate problems 0.2 only. He will give it. I have not seen any gate problem where he does not give. Suppose he does
sir,
not give, maybe the transistor is inactive.
Okay.
Okay.
Okay, sir. That can happen, sir. Yes, sir. Okay, this was doubt. Okay, thank you, sir. Thank you.
Right.
Hello, sir.
Yes.
Sir, can you please explain about Q points?
Your voice is low. Tell me.
Sir, can you please explain about Q points, sir?
Q point.
Yes, sir.
Q point means when you give a DC voltage to a circuit, some DC current will flow, no? That is Q point.
Okay, sir.
All these are Q points only. All these are Q points. So for a transistor, what is Q point? On the output characteristics. It is its VC, IC. What VC and what IC the transistor is giving, that is Q point. Because on a graph, you need X and Y, no? Point means X, Y is a point. Can you see?
Yes, sir.
X-axis is VC, Y-axis is IC. So if you find VC and IC, that means you have found Q point. This I will explain in biasing. After this topic, we have biasing, no?
Sir, then every point is Q point itself.
Yeah, every DC voltage. Once you give DC voltage, DC currents are flowing. Q, the word Q stands for quiescent. Quiescent stands for static. Static means DC. See, I have this knee problem. When I went to the doctor, I asked the doctor, sir, please stop medicine. He says, no, you have to continue for another 3-4 months. The problem seems to be quiescent, he said. I asked him, sir, what? The problem seems to be quiescent. That means right now it is static. It is constant. Slowly it will become dynamic. So quiescent is an opposite word for dynamic. It is static. Static means what? The voltage and currents that does not change. When the voltage and current will not change, only for DC.
DC.
Yeah.
Thank you, sir.
Okay.
Hello, sir.
Yeah.
Sir, once again explain that early effect, sir.
Early effect.
Yes, sir.
Just now I explained, no? Early effect means if VC changes, then your VCB will change. If VCB changes, then the base width is going to reduce. Whenever base width keeps on changing, IC will not be same. Sometimes if that's what I gave you an analogy, no? If few soldiers have started, if all the time same people die, if all the time your IB is same, your IC will be same. But your IB is not same when VCB changes. Because the base width is different. See, it's almost like the transistor is behaving as if there are so many transistors. Are you getting? The characteristics of the transistor is what? The VCB keeps on changing. It's like a different device, no? A different device with a different base width, different collector current. So when VCB changes, your effective base width will also keep on changing. That is why the IC keeps on changing. But don't worry, in analog, we are going to make that constant.
Sir, by diagrammatic, can you explain?
Diagrammatica? No, first, you should know how to draw these dabba here. Yeah. See, you have to draw like this. Okay. One is emitter. 3 boxes you have to put. This is emitter. base collector. This is an NPN transistor, NPN. Between N and P, there is a barrier. Here you can use a different color for barrier. So here, once N and P, you sandwich them, they are depleted of charges. Yes or no?
Yeah.
So now what is working? The one that is in usage is this part, and this part. What is the other, the gap here? That is the depletion. Yes or no?
Yes, sir.
Now what I'm saying is this part can increase now. Suppose this is because of 4.3 volt. That part can increase now. This part, this 4.3, it can increase.
Okay, sir, I understood.
Yeah, now the depletion can increase because of 8.3 volt now. Yes or no? So what is the part that is usage? This is the emitter, where there are holes and electrons. This collector. Now this is your base width. So this is less width, no? This is more width.
Yes, yes.
Yes.
Thank you.
Electrons try to travel here. The base current here is going to be less. Here there will be less IB. IB means loss, no?
Yes, sir.
Here more IC will be there, more IC. So here less IC. That we can see here like this. For 8.3 more IC. For 4.3 less IC. Yes or no?
Yes, sir.
Yeah.
Thank you, sir.
Yeah. Yeah. Tell me. Can you hear me? Can you hear me? What happened this? Ask to unmute.
Sir, I have asked, sir.
Yeah. Can you hear me now?
Hello, sir.
Yeah.
Hello, sir. Page number 28, sir. Sir, VC value is standard value, sir.
VC will change based on the circuit, no? 1 volt, 2 volt, 5 volt. VC saturation is standard.
VCE, sir.
VCE saturation is 0.2. VC collector will always be greater than emitter, no?
Yes, sir.
Based on the resistor values, it will change.
Yes, sir.
Yeah.
And sir, and that soldier explanation is very nice, sir. I understood that concept.
Which one?
That soldier thing you have explained, no, sir.
Yeah.
That is very nice. And sir, one more doubt is beta forced. What is significance of beta forced?
Beta force means that the transistor is no longer useful for amplifier. If you force a low value of beta, because BJT means what? There should be some amplification, no? Beta should be there. If you force a large base current and collector current is small, then what will happen? BJT is useless for amplifier. You cannot design voltage amplifier, current amplifier, transconductance, no amplifier you can design. Then you can use it for digital logic. Digital guys, they like this 0.2. They treat that 0.2 as logic 0.
Okay, sir.
Logic 0. And open circuit, if a high voltage 10 volt it appears here, they might treat it as logic 1. So cutoff region directly 10 volt, saturation region 0.2. So this 0.2 is for logic 0, 10 volt is for logic 1. They will use cutoff and saturation for logic 0 and logic 1. Are you getting? So this 0.2
Yes, sir. Yes, sir.
useless for analog.
Okay, sir.
Yeah.
Got it, sir. Sir, sir, how to differentiate between NPN and PNP, sir?
How to differentiate between NPN and PNP?
Hello?
In the sense, arrow is there, no? The symbol you're asking, huh? Symbol, this is an
Yes, sir.
NPN.
Getting confused. Like in question, if they given.
Acha, see, if the arrow is up, it is PNP. If the arrow is down, it is NPN. This is P and P.
Arrow is down, then.
Yeah, arrow, this one is PNP.
Okay, sir. If arrow is down, then.
This is NPN. Or you can treat it like this. If the arrow leaves, it is NPN. If the arrow enters, it is PNP. Are you getting? This is IE. Yeah.
Hello, sir.
Yes.
Sir, yesterday you said the diode is not an amplifier, no, sir.
Yes.
But today you have compared that BJT is a good amplifier. Between BJT and diode, you have compared. No?
Only switch is compared, no? Not amplification.
You said about amplifier also. No?
Yeah, I told it is useless because it gives microampere of current. It is just a passive element.
Correct.
Yeah.
Okay.
Okay. Still.
Sir, good evening, sir.
Yes.
Sir, hello.
Yeah, tell me.
ఈ ఈవర్స్ మోడల్ ఇక్కడ అనలాగ్ లో చెప్తారా లేకపోతే ఈడిసి లో కవర్ చేయాలి సార్ అందుకని.
ఏం మోడల్ అండి? వాట్ మోడల్?
ఈవర్స్ రోల్ మోడల్ ఉంటుంది సార్, డయోడ్ మనం ఇట్లా.
EDC they might cover, but if you want, we will see in analog. See, what is more important for us is the model which is useful for amplifiers. So the pi model and T model we will use. Ebers mode model is the diode model kada adi. Crude model వాళ్ళు అక్కడ యూజ్ చేస్తే ఓకే, లేదు అంటే మనం చూద్దాం, అసలు అవసరం లేదు. ఎబర్స్ మోడ్ అది పాత మోడల్, ఇప్పుడు అవి వాడట్లేదు కదా మనము.
ఓకే అంటే లేదు సార్, అది మన వర్క్ బుక్ లో ఉంటే అది అక్కడ సార్ అడిగితే అక్కడ అన్నారు
మోడల్ అండి అవి. ఇప్పుడు మనకి ఏది యూస్ఫుల్ అంటే పై మోడల్ కానీ టీ మోడల్ కానీ వాడతాం మనం.
ఓకే సార్. ఓకే సార్.
ఆ పై మోడల్ టీ మోడల్ బెనిఫిట్ ఏంటంటే, వాట్ ఈస్ ద బెనిఫిట్ ఈస్ ఇఫ్ బై సీయింగ్ ఎ సర్క్యూట్ యూ కెన్ టెల్ ద ఆన్సర్.
Okay,
even if there are 10 transistor, 20 transistor, by seeing you can tell. So it is very popular. For Ebersmall model, even for a single BJT you have to struggle.
Yes sir, diode connected fashion analysis చాలా కష్టం.
So it is crude form, so not needed. Our main aim ఏంటి, మనకి 10 ట్రాన్సిస్టర్లు ఇచ్చినా తప్పని ఆన్సర్ చెప్పాలి, అది మనకి.
సార్ ఇంకొకటి సార్, ఈ ఇందులో కొంచెం డౌట్ సార్, ఈడీసీ మనకి స్పెషల్ పర్పస్ డయోడ్ ఉంటాయి కదా సార్, ఫోటో డయోడ్, ఎల్ఈడి ఇవన్నీ.
అవి నాకు సంబంధం
లేదు సార్, అది తెలుసు సార్, కానీ ఎక్కడన్నా సోర్స్ ఉంటుందా సార్ మంచి చదువుకోవడానికి? అప్పుడు ఎన్ని బుక్స్ కొంచెం టఫ్ ఉన్నాయి.
నేను కనుక్కుంటానండి. ఏమేమి టాపిక్లు కావాలి మీకు అందులో?
ఇదే సార్, ఈ స్పెషల్ పర్పస్ డయోడ్ సార్, ఫోటో డయోడ్స్, ఎల్ఈడి ఉంటాయి కదా సార్, కొంచెం తెలిస్తే సార్. ఇంకొకటి సార్, కొంచెం మీకు టైం ఒకవేళ కుదిరితే ఇప్పుడు బ్రేక్ డౌన్ వోల్టేజ్ ఉంటుంది కదా సార్ మనకి బీజేటీకి, అది
చెప్పండి. బ్రేక్ డౌన్
ఒకవేళ టైం మీకు కుదిరితే కొంచెం ఆ బ్రేక్ డౌన్ వోల్టేజ్ ఉంటుంది కదా సార్, మనం బ్రేక్ డౌన్ వోల్టేజ్ కనుక్కుంటాం కదా సార్. కొంచెం అదొక్కటి వీలైతే చూడండి సార్.
చేయమంటారా? బ్రేక్ డౌన్
లేదు సార్. ఎస్ సార్, కొంచెం ఒక్కటి సార్ ఏదన్నా అంటే అట్లా బ్రేక్ డౌన్ వోల్టేజ్ ఎలా ఏంటి.
నాకు వాట్సాప్ పంపించండి.
ఓకే సార్, ఓకే సార్.
నాకు నేను ఏదన్నా ఉంటే ఐ గెట్ బ్యాక్ టు యూ. ఓకే,
ఓకే సార్,
మీకు చూసి అడుగు చెప్తాను నేను.
ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్ సార్. థ్యాంక్ యూ సో మచ్ సార్. నా పేరు సమరసింహారెడ్డి సార్.
ఓకే
ఎస్ సార్, థ్యాంక్ యూ సార్.
Yes. Anybody else?
Completed sir, completed for me sir.
Okay, thank you.
Thank you sir. Good night sir.
Right, good night. Yeah, sweetie, come inside.
My God.